A theory of everything, often abbreviated as 2E, is a hypothetical framework that seeks to explain all fundamental aspects of the universe in a single, all-encompassing, coherent model. It aims to unify the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Essentially, a 2E would provide a complete, self-consistent explanation of the physical phenomena in the universe. The quest for a theory of everything represents one of the most ambitious goals in physics. Scientists have been striving to reconcile the seemingly incompatible theories of general relativity and quantum mechanics. General relativity describes the force of gravity and the structure of space-time on a large scale, while quantum mechanics explains the behavior of particles at the smallest scales. A 2E would bridge the gap between these two foundational theories. Historically, the concept of unifying different forces in nature dates back to ancient philosophical inquiries about the fundamental nature of reality. However, it gained scientific traction in the 20th century with advances in quantum theory and relativity. The term theory of everything itself became popularized in the late 20th century as physicists began to seriously entertain the possibility of such a comprehensive theory. One of the main challenges in developing a theory of everything is finding a mathematical framework that can describe both the macroscopic realm of general relativity and the microscopic realm of quantum mechanics. These realms operate on vastly different scales and exhibit different behaviors, making unification a complex task. The equations of general relativity, for instance, are smooth and continuous, while quantum mechanics relies on discrete probabilities. Several candidate theories have been proposed over the years, with string theory being one of the most prominent. String theory posits that the fundamental particles we observe are not point-like objects, but rather tiny, vibrating strings. These strings can vibrate at different frequencies, giving rise to the various particles and forces in the universe. String theory suggests that the different vibrations of these strings correspond to the different fundamental forces and particles. Another approach is loop quantum gravity, which attempts to quantize space-time itself. In loop quantum gravity, space-time is not continuous, but consists of discrete chunks, much like the quantized nature of energy levels in atoms. This theory provides a way to reconcile the smooth space-time of general relativity with the discrete quantum states of quantum mechanics. However, it remains an area of active research and debate. In addition to these theories, there are also grand unified theories, or GUTs, which aim to unify the strong, weak, and electromagnetic forces, but do not yet include gravity. GUTs propose that at high energy levels, such as those present just after the Big Bang, these three forces were unified into a single force. As the universe cooled, they separated into the distinct forces we observe today. The holographic principle offers another intriguing avenue for a theory of everything. This principle suggests that all the information contained within a volume of space can be represented as a hologram, a two-dimensional surface that encodes the three-dimensional information. This idea has profound implications for our understanding of space, time, and information, potentially linking quantum mechanics and gravity. Twistor theory, developed by Roger Penrose, provides a mathematical framework that may contribute to a TOE. Twistor theory reimagines the fundamental objects of space-time and could offer insights into the unification of quantum mechanics and general relativity. However, it remains a highly abstract and complex field of study. Non-commutative geometry, another candidate, alters the traditional notion of space-time by allowing the coordinates of space to become operators that do not commute. This approach introduces a new way of thinking about the fabric of the universe and could pave the way for a unified theory. Emergent gravity theories propose that gravity is not a fundamental force, but an emergent phenomenon arising from the microscopic behavior of particles. These theories suggest that gravity, as we experience it, is a result of deeper, underlying processes at the quantum level. This perspective challenges conventional views and opens new possibilities for unification. Quantum loop topography explores the idea that the fundamental structure of space-time can be understood through the properties of loops and knots at the quantum level. This approach seeks to describe the geometry of space-time in a way that is consistent with both quantum mechanics and general relativity. The idea of a theory of everything also raises profound philosophical questions about the nature of reality and our place in the universe. If such a theory were found, it would represent a culmination of centuries of scientific inquiry and have far-reaching implications for our understanding of existence. The search for a TOE is as much a quest for knowledge as it is a journey into the unknown. The implications of discovering a theory of everything would extend beyond physics, potentially impacting other scientific fields, technology, and even our philosophical and existential perspectives. It would provide a framework for understanding the universe at its most fundamental level, potentially leading to new technologies and insights into the nature of consciousness and reality itself. As physicists continue to explore these various theories and ideas, the pursuit of a theory of everything remains one of the most exciting and challenging frontiers in science. Each new discovery brings us closer to understanding the fundamental principles that govern the universe, offering the promise of a deeper and more unified understanding of the cosmos. A theory of everything is essential because it represents the pinnacle of our understanding of the universe, encapsulating all fundamental forces and particles within a single, coherent framework. The significance of such a theory extends beyond mere academic interest. It promises to revolutionize our grasp of the cosmos and our place within it. Physicists view the pursuit of a TOE as a way to unify the two pillars of modern physics, general relativity and quantum mechanics. These theories describe vastly different scales, with relativity governing the cosmos and quantum mechanics explaining subatomic particles. A TOE would bridge this gap, offering a unified description of all physical phenomena. The search for a TOE also has profound implications for our understanding of fundamental forces. Currently, we know of four: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. A TOE would show how these forces are different manifestations of a single underlying principle, potentially simplifying and unifying our understanding of the universe. By providing a comprehensive explanation of the universe, a TOE would also address the inconsistencies and anomalies that current theories cannot explain. For instance, the incompatibility between general relativity and quantum mechanics leads to singularities, like those at the centers of black holes, where our current laws of physics break down. A TOE could resolve these issues, offering a complete picture of how the universe works. Moreover, a theory of everything would have practical implications, potentially leading to new technologies and advancements. Just as the understanding of electromagnetism in the 19th century led to the development of technologies like radio, television, and the internet, a TOE could unlock new realms of technological innovation, perhaps in ways we cannot yet imagine. The pursuit of a TOE also drives theoretical and experimental physics forward. The challenges and questions it raises push physicists to develop new mathematical tools, conduct novel experiments, and explore uncharted territories in both theory and practice. This relentless pursuit of knowledge fuels scientific progress and inspires new generations of scientists. A unified theory could also offer new insights into the early universe, providing a clearer understanding of the conditions just after the Big Bang. By explaining how all forces and particles interacted in those extreme conditions, a TOE would illuminate the birth and evolution of the cosmos, shedding light on the origins of matter, energy, and the fundamental structures of the universe. Furthermore, a theory of everything holds the promise of answering some of the most profound philosophical questions about the nature of reality. It would offer a framework for understanding why the universe is the way it is, potentially revealing deeper truths about existence and the laws governing all phenomena. In addition to its scientific and philosophical significance, a TOE would have educational implications, offering a more straightforward way to teach and understand the complexities of the universe. By unifying the various branches of physics, it would provide a coherent framework that makes learning about the cosmos more accessible and intuitive. The search for a theory of everything also exemplifies the human drive to seek knowledge and understanding. It reflects our innate curiosity and our desire to make sense of the world around us, embodying the spirit of scientific inquiry and the quest for truth. Despite the challenges and obstacles, the pursuit of a TOE is driven by the belief that the universe is ultimately comprehensible. This conviction motivates physicists to continue their efforts, knowing that each step brings us closer to uncovering the ultimate laws of nature. The journey toward a theory of everything is also a collaborative endeavor, involving physicists from around the world working together to solve one of the greatest scientific challenges of our time. This global effort highlights the importance of international collaboration and the shared goal of advancing our understanding of the universe. Moreover, the development of a TOE would have a profound impact on our worldview, potentially reshaping our understanding of humanity's place in the cosmos. It could change how we perceive ourselves and our relationship to the universe, offering a deeper sense of connection to the natural world. Finally, a theory of everything would provide a foundation for future scientific exploration and discovery. By offering a complete and unified description of the universe, it would serve as a launching pad for new lines of inquiry and investigation, opening up new frontiers in physics and beyond. The quest for a theory of everything has deep historical roots, tracing back to ancient Greek philosophers like Democritus, who first imagined that everything is made of indivisible atoms. They sought a fundamental explanation for all natural phenomena, laying the groundwork for future scientific inquiry. During the scientific revolution of the 17th century, the development of classical mechanics by Isaac Newton marked a significant milestone. Newton's laws of motion and universal gravitation provided a comprehensive framework for understanding the physical world, unifying terrestrial and celestial mechanics. In the 19th century, James Clerk Maxwell's equations unified electricity and magnetism into a single theory of electromagnetism. This was a monumental step toward a unified description of nature, showing that seemingly distinct forces could be described by a common set of principles. The early 20th century witnessed the emergence of quantum mechanics and the theory of relativity. Albert Einstein's work on special and general relativity revolutionized our understanding of space, time, and gravity, while pioneers like Niels Bohr and Werner Heisenberg developed quantum mechanics, explaining the behavior of particles on the smallest scales. Despite their successes, relativity and quantum mechanics were fundamentally incompatible. The equations of general relativity, which describe the curvature of space-time, clashed with the probabilistic nature of quantum mechanics. This incompatibility set the stage for the search for a theory of everything. In the 1970s, the development of the Standard Model of particle physics brought significant progress. It successfully described 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, using quantum field theory. However, gravity remained outside this framework. The introduction of string theory in the late 20th century offered a promising approach. Instead of point particles, string theory proposed that the fundamental constituents of the universe are tiny, vibrating strings. This theory aimed to unify all forces and particles by describing them as different modes of string vibration. Stephen Hawking and other physicists began exploring the implications of black hole thermodynamics, suggesting a deep connection between quantum mechanics, thermodynamics, and general relativity. These investigations hinted at a more profound underlying theory that could unify these disparate areas. In the 1980s and 1990s, efforts to develop a grand unified theory, GUT, sought to merge the electromagnetic, weak, and strong forces into a single theoretical framework. While successful to an extent, these theories still struggled to incorporate gravity. Loop quantum gravity emerged as another contender, proposing that spacetime itself is quantized. This theory aimed to reconcile the smooth structure of general relativity with the discrete nature of quantum mechanics, offering an alternative to string theory. The holographic principle, inspired by studies of black holes and information theory, suggested that all the information within a volume of space could be encoded on its boundary. This principle has profound implications for unifying quantum mechanics and gravity. Emerging theories like twistor theory and non-commutative geometry explored new mathematical frameworks for unification. These approaches offered innovative ways to rethink the fundamental nature of space, time, and particles, pushing the boundaries of conventional physics. Throughout history, the pursuit of a theory of everything has driven physicists to develop new tools and concepts, from the calculus of Newton to the quantum field theories of the 20th century. Each step has brought us closer to understanding the fundamental nature of reality. As we look back at the historical context and origins of this quest, it's clear that the search for a theory of everything is not just a scientific endeavor, but a continuation of humanity's age-old desire to comprehend the cosmos. This journey reflects our deepest curiosity and our relentless pursuit of knowledge. Currently, research into a theory of everything is advancing on multiple fronts, with various theoretical frameworks being explored. String theory remains one of the leading candidates, continuing to evolve with new insights and mathematical developments. Researchers are investigating its implications for black holes, cosmology, and particle physics. Loop quantum gravity also garners significant attention, offering a different approach to unifying general relativity and quantum mechanics. Scientists are working on refining the theory and exploring its predictions for the early universe and the nature of space-time. In addition to these primary frameworks, researchers are delving into the holographic principle, particularly the ad-SR-CFT correspondence. This idea, suggesting that a lower dimensional theory can describe a higher dimensional universe, is opening new avenues in theoretical physics. Grand unified theories are still under intense scrutiny. Physicists aim to identify experimental evidence that could validate or refute these models, focusing on high-energy particle collisions and proton decay experiments. Another area of active research involves non-commutative geometry. By rethinking the fundamental structure of spacetime, this approach could offer a path to unification, though it remains highly theoretical and abstract. Twistor theory, although less mainstream, is making strides in connecting quantum mechanics and general relativity. Researchers are developing new mathematical techniques to explore its potential for describing fundamental particles and forces. Experimental physics plays a crucial role in testing these theories. The Large Hadron Collider, LHC, and other particle accelerators are at the forefront, probing the high-energy regimes where unification might become apparent. These experiments aim to detect phenomena that current theories predict, such as supersymmetry or extra dimensions. Cosmological observations also provide vital data. The study of the cosmic microwave background radiation, galaxy formation, and dark matter distribution helps test predictions made by various unification theories. These observations are crucial for refining and validating theoretical models. Quantum computing and quantum information theory are emerging as valuable tools in this quest. These fields offer new ways to simulate and understand complex quantum systems, potentially revealing insights into the unification of forces. Collaborative efforts among physicists, mathematicians, and computer scientists are essential. Interdisciplinary research is leading to innovative approaches and fresh perspectives on long-standing problems in theoretical physics. While significant progress has been made, many challenges remain. The mathematical complexity of unification theories requires new methods and tools, and experimental validation is still in its early stages. Despite these hurdles, the research community remains optimistic. New experimental facilities, such as next-generation particle accelerators and space-based observatories, promise to provide more data and higher precision measurements. These advancements are expected to shed light on the fundamental forces and particles that make up our universe. Theoretical breakthroughs are also on the horizon. Novel ideas and unexpected discoveries continue to reshape our understanding of physics, driving the search for a theory of everything forward. Each new insight builds upon decades of research and collaboration. As researchers continue to explore the frontiers of physics, the goal of a unified theory remains a guiding light. The pursuit itself pushes the boundaries of human knowledge, leading to technological innovations and deeper understanding of the universe. The current state of research into a theory of everything is vibrant and dynamic. It represents a global effort to uncover the fundamental laws of nature, reflecting our collective quest to comprehend the cosmos at its most basic level. In this video, we'll embark on a comprehensive journey through the quest for a theory of everything. We'll start by defining what a theory of everything, or 2E, actually means and why it's such a pivotal concept in physics. We'll then delve into the historical context and origins of the quest for a unified theory, exploring how ancient philosophical inquiries evolved into the sophisticated scientific endeavors of today. Understanding the past will set the stage for grasping the current state of research. From there, we'll examine the classical physics foundations that laid the groundwork for modern theories. This includes Newtonian mechanics, electromagnetism, and thermodynamics, and how these classical theories paved the way for later breakthroughs. Next, we'll cover the revolutionary impact of relativity theory, introduced by Albert Einstein. We'll discuss both special and general relativity, exploring how these theories transformed our understanding of space, time, and gravity. Quantum mechanics will be our next major topic. We'll explore the fundamental principles of quantum theory, such as wave-particle duality, the uncertainty principle, and quantum entanglement, and how these ideas challenge classical physics. We'll then transition to quantum field theory, which extends quantum mechanics to fields and particles. This section will highlight the development of the standard model of particle physics and the unification of electromagnetism, the strong nuclear force and the weak nuclear force. String theory will be a major focus, offering one of the most prominent frameworks for a TOE. We'll explain the basic concepts of string theory, its different types, and its potential to unify all fundamental forces and particles. Loop quantum gravity presents an alternative approach to unification. We'll explore how this theory attempts to quantize space-time itself, providing a different path to reconciling general relativity and quantum mechanics. M-theory, an extension of string theory, will be covered next. We'll discuss how it seeks to unify various string theories into a single framework, and the role of higher dimensions and brains in this grand unification effort. Grand unified theories, or GUTs, will be another critical topic. We'll explore how these theories aim to merge the strong, weak, and electromagnetic forces and the experimental efforts to detect evidence supporting these models. The holographic principle offers a fascinating perspective on unification. We'll explain how this idea suggests that all the information in a volume of space can be encoded on its boundary and its implications for quantum gravity. We'll also look at emerging theories and ideas that could contribute to a TOE, including twistor theory, non-commutative geometry, emergent gravity, and quantum loop topography. These innovative approaches push the boundaries of our understanding. The importance of experimental physics in testing these theories cannot be overstated. We'll highlight the role of particle accelerators, cosmological observations, and new experimental technologies in providing data that could confirm or refute theoretical predictions. Throughout the video, we'll emphasize the collaborative nature of this quest. Scientists from around the world across various disciplines are working together to solve one of the greatest challenges in science, driven by a shared curiosity and determination. Finally, we'll reflect on the broader implications of discovering a theory of everything. This pursuit not only seeks to unify our understanding of the universe, but also inspires new questions and possibilities, continuing the never-ending journey of scientific exploration. Newtonian mechanics forms the foundation of classical physics, describing the motion of objects and the forces acting upon them. Developed by Sir Isaac Newton in the 17th century, it introduced key concepts that revolutionized our understanding of the physical world. At the core of Newtonian mechanics are Newton's three laws of motion. These laws explain how objects move in response to forces, providing a comprehensive framework for analyzing motion. The first law, often called the law of inertia, states that an object will remain at rest or in uniform motion unless acted upon by a net external force. The second law of motion, perhaps the most famous, quantifies the relationship between force, mass, and acceleration. It states that the force acting on an object is equal to the mass of that object multiplied by its acceleration. This principle allows us to predict how objects will move under various forces. Newton's third law of motion is equally important, stating that for every action, there is an equal and opposite reaction. This law explains the interactions between objects, from the recoil of a gun to the propulsion of rockets, highlighting the symmetry and physical forces. Central to Newtonian mechanics is the concept of gravity. Newton's law of universal gravitation posits that every mass attracts every other mass, with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This groundbreaking idea explained both earthly phenomena and the motions of celestial bodies. Newtonian mechanics also introduced the concept of momentum, defined as the product of an object's mass and velocity. The conservation of momentum is a key principle, stating that in a closed system, the total momentum remains constant unless acted upon by external forces. Another crucial concept is kinetic energy, the energy of motion, and potential energy, the energy stored due to an object's position. The principle of conservation of energy states that the total energy in a closed system remains constant, merely transforming between kinetic and potential forms. The mathematical formulation of Newtonian mechanics relies on calculus, which Newton himself co-developed. This powerful mathematical tool allows for precise predictions of motion and dynamics, enabling the analysis of complex systems. Newtonian mechanics successfully described a wide range of phenomena, from the motion of planets and the behavior of projectiles to the dynamics of machines and structures. It provided a unified framework that was both predictive and explanatory. However, Newtonian mechanics has its limitations. It assumes that time and space are absolute, and that forces act instantaneously at a distance. These assumptions were later challenged by the theories of relativity and quantum mechanics, which revealed deeper layers of physical reality. Despite these limitations, Newtonian mechanics remains highly relevant. It accurately describes the motion of everyday objects and continues to be the basis for engineering, astronomy, and many other fields. Its principles are taught as the foundation of physics education. In modern physics, Newtonian mechanics is often used as an approximation for systems where relativistic and quantum effects are negligible. It provides a first-order understanding that can be refined with more advanced theories when necessary. The legacy of Newtonian mechanics extends beyond physics. It laid the groundwork for the scientific method, emphasizing empirical observation, mathematical description, and predictive power. Newton's approach set the standard for scientific inquiry. The impact of Newtonian mechanics on technology and society cannot be overstated. It enabled the development of machinery, navigation, and countless technological advancements, driving the Industrial Revolution and shaping the modern world. Newtonian mechanics represents a monumental achievement in human understanding, offering a clear and powerful description of the physical world. Its principles continue to inform and inspire, forming the bedrock upon which much of modern science is built. Electromagnetism is one of the four fundamental forces of nature, governing the behavior of charged particles. It unifies electricity and magnetism into a single, coherent theory. The study of electromagnetism began in earnest in the 19th century, with key contributions from scientists like Michael Faraday and James Clerk Maxwell. Michael Faraday discovered that a changing magnetic field can induce an electric current, a principle known as electromagnetic induction. This discovery laid the foundation for electric generators and transformers, revolutionizing the generation and distribution of electricity. James Clerk Maxwell made a groundbreaking contribution by formulating Maxwell's equations. These four equations describe how electric and magnetic fields are generated and altered by each other and by charges and currents. Maxwell's work unified the previously separate fields of electricity and magnetism. Maxwell's equations also predicted the existence of electromagnetic waves, which travel at the speed of light. This revelation led to the understanding that light itself is an electromagnetic wave, encompassing a broad spectrum that includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The realization that light is an electromagnetic wave profoundly impacted our understanding of the universe. It bridged the gap between optics and electromagnetism, showing that the same principles govern phenomena as diverse as radio transmissions and the behavior of light. Electromagnetic waves have a wide range of applications in modern technology. Radio waves enable communication over vast distances, microwaves power radar and cooking devices, and X-rays are essential in medical imaging. The entire electromagnetic spectrum is harnessed in various ways to improve our lives. Electromagnetism also plays a crucial role in the atomic and molecular structure. The electromagnetic force binds electrons to the nucleus in atoms, determining the chemical properties of elements. This force is responsible for the interactions between atoms and molecules, which are the basis of chemistry and biology. In addition to its technological applications, electromagnetism has deep theoretical significance. It provided a framework that helped lead to the development of quantum mechanics and special relativity. The interplay between electric and magnetic fields is central to many fundamental processes in nature. The discovery of the electron by J.J. Thomson and the development of quantum theory expanded our understanding of electromagnetism. Quantum electrodynamics, or QED, describes how light and matter interact at the quantum level, incorporating the principles of both quantum mechanics and special relativity. QED has been remarkably successful in predicting the outcomes of experiments with extraordinary precision. It is one of the most accurate theories in physics, demonstrating the power of the electromagnetic theory at the smallest scales. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga were awarded the Nobel Prize for their contributions to QED. Electromagnetic theory also laid the groundwork for the development of modern technologies, such as semiconductors, lasers, and fiber optics. These innovations are fundamental to contemporary electronics, communication systems, and medical devices. One of the profound insights of electromagnetism is the concept of electromagnetic fields. These fields extend through space and can carry energy and momentum. The study of these fields has led to a deeper understanding of the nature of forces and interactions in the universe. The unification of electromagnetism with the weak nuclear force into the electroweak theory by Sheldon Glashow, Abdus Salam, and Steven Weinberg was a major milestone. This unification demonstrated that at high energies, these two forces are aspects of a single fundamental force. Electromagnetism continues to be a vibrant field of research, with ongoing studies into advanced materials, photonics, and quantum information. Understanding and manipulating electromagnetic phenomena are key to many future technological advancements. The profound impact of electromagnetism on science, technology, and our daily lives underscores its importance. From powering our homes to enabling global communication, the principles of electromagnetism are integral to the modern world, reflecting the deep connections between fundamental physics and practical applications. Thermodynamics is a branch of physics that deals with heat, work, and energy. It describes how energy is transferred and transformed, playing a crucial role in understanding both natural processes and engineered systems. The foundations of thermodynamics were laid in the 19th century, primarily through the work of scientists such as Sadi Carnot, Rudolf Clausius, and Lord Kelvin. The first law of thermodynamics, also known as the law of energy conservation, states that energy cannot be created or destroyed, only transferred or converted from one form to another. This principle underpins the concept of energy conservation, emphasizing that the total energy of an isolated system remains constant. The second law of thermodynamics introduces the concept of entropy, a measure of disorder or randomness in a system. It states that the total entropy of an isolated system can never decrease over time. This law implies that natural processes tend to move towards a state of greater disorder and that energy conversions are never perfectly efficient. The third law of thermodynamics states that as the temperature of a system approaches absolute zero, the entropy of the system approaches a minimum value. This law highlights the unattainability of absolute zero, as reaching it would require removing all thermal energy from a system, which is impossible. Thermodynamics is fundamental to understanding heat engines, devices that convert thermal energy into mechanical work. The efficiency of heat engines is governed by the second law of thermodynamics, which sets limits on the maximum possible efficiency, known as the Carnot efficiency. The concept of thermodynamic equilibrium is central to this field. A system in thermodynamic equilibrium has no net flow of energy or matter, and its macroscopic properties remain constant over time. Understanding equilibrium conditions is essential for analyzing chemical reactions, phase transitions, and other processes. Thermodynamic cycles, such as the Carnot cycle and the Rankine cycle, are models that describe the operations of heat engines and refrigerators. These cycles illustrate the principles of energy conversion and provide insights into the performance and efficiency of real-world systems. The study of thermodynamics extends to statistical mechanics, which links the microscopic behavior of individual particles to the macroscopic properties of materials. Statistical mechanics provides a deeper understanding of entropy and temperature by considering the statistical behavior of particles in a system. Thermodynamics also plays a crucial role in chemistry, particularly in the study of chemical reactions and phase changes. The principles of thermodynamics help predict the direction of chemical reactions, the equilibrium state of mixtures, and the energy changes associated with these processes. In biology, thermodynamics is essential for understanding metabolic processes and energy transfer within living organisms. It explains how organisms convert food into energy, maintain homeostasis, and regulate their internal environments to sustain life. Thermodynamic principles are vital in engineering, particularly in the design and analysis of power plants, refrigeration systems, and engines. Engineers use these principles to optimize energy efficiency, reduce waste, and develop sustainable technologies. The concept of free energy, including Gibbs free energy and Helmholtz free energy, is critical in thermodynamics. Free energy measures the useful work obtainable from a system at constant temperature and pressure, helping predict the spontaneity of processes and reactions. Thermodynamics also addresses the properties of different states of matter, such as solids, liquids, and gases. It explains phase transitions, like melting, boiling, and sublimation, and the conditions under which these transitions occur. The study of non-equilibrium thermodynamics extends these principles to systems that are not in equilibrium, providing insights into complex phenomena such as heat transfer, diffusion, and chemical kinetics. This field is crucial for understanding and designing processes that operate far from equilibrium. In the context of the universe, thermodynamics plays a role in cosmology and the study of black holes. The laws of thermodynamics apply to black hole entropy and Hawking radiation, linking the behavior of these cosmic objects to fundamental thermodynamic principles. Thermodynamics is a cornerstone of physics and engineering, offering a comprehensive framework for understanding energy transformations and the behavior of systems. Its principles are integral to a wide range of scientific and practical applications, highlighting the interconnectedness of natural laws and technological advancements. Classical wave theory is essential for understanding how waves propagate through different media. It describes the behavior of mechanical waves, such as sound and water waves, and electromagnetic waves, including light and radio waves. This theory provides a framework for analyzing wave phenomena and their interactions with matter. A wave is a disturbance that travels through a medium, transferring energy from one point to another without transporting matter. Waves can be classified as transverse or longitudinal. In transverse waves, the displacement of the medium is perpendicular to the direction of wave propagation, while in longitudinal waves, the displacement is parallel. The fundamental properties of waves include wavelength, frequency, amplitude, and speed. Wavelength is the distance between successive crests or troughs of a wave. Frequency is the number of wave cycles that pass a given point per unit of time, usually measured in hertz. Amplitude is the maximum displacement of the medium from its equilibrium position, and wave speed is the rate at which the wave propagates through the medium. One of the key principles of wave theory is superposition. When two or more waves meet, their displacements add together, resulting in constructive or destructive interference. Constructive interference occurs when wave crests or troughs align, amplifying the wave, while destructive interference occurs when crests align with troughs, reducing the wave's amplitude. Reflection, refraction, and diffraction are fundamental behaviors of waves. Reflection occurs when a wave encounters a boundary and bounces back. Refraction involves the change in wave direction as it passes from one medium to another due to a change in wave speed. Diffraction is the bending of waves around obstacles or through openings, spreading out as they propagate. The Doppler effect is a significant phenomenon in wave theory. It describes the change in frequency or wavelength of a wave in relation to an observer moving relative to the wave source. This effect is commonly observed with sound waves, such as the change in pitch of a passing siren, and with electromagnetic waves, influencing astronomical observations. Sound waves are longitudinal mechanical waves that travel through gases, liquids, and solids. The speed of sound depends on the medium's properties, such as density and elasticity. In air, sound travels at approximately 343 meters per second at room temperature. Sound waves are essential for communication, music, and many technologies. Water waves are surface waves that occur at the interface between water and air. These waves result from the interaction of gravitational forces and surface tension. They exhibit complex behaviors, including reflection, refraction, and diffraction, and are influenced by factors like wind, currents, and water depth. Electromagnetic waves are transverse waves that do not require a medium, allowing them to propagate through a vacuum. They encompass a broad spectrum, from radio waves to gamma rays, with visible light being a small part of this spectrum. Electromagnetic waves are crucial for communication, medical imaging, and various technologies. The principle of wave-particle duality emerged from the study of light. Classical wave theory described light as a wave, explaining phenomena like interference and diffraction. However, experiments like the photoelectric effect revealed light's particle-like behavior, leading to the development of quantum mechanics. Wave optics, or physical optics, deals with the wave nature of light. It explains phenomena such as interference patterns, diffraction, and polarization. These principles are critical for understanding the behavior of light in various applications, including lenses, microscopes, and optical instruments. Standing waves are a particular type of wave pattern that occurs when two waves of the same frequency and amplitude travel in opposite directions and interfere. This interference creates nodes, points of zero amplitude, and antinodes, points of maximum amplitude. Standing waves are significant in musical instruments, resonant cavities, and waveguides. Resonance occurs when a system is driven at its natural frequency, resulting in a significant increase in amplitude. This phenomenon is observed in musical instruments, bridges, and even in molecular vibrations. Understanding resonance is vital for designing stable structures and tuning systems. Group velocity and phase velocity are important concepts in wave theory. Phase velocity is the speed at which individual wave crests or troughs move, while group velocity is the speed at which the overall shape of a wave pulse or wave packet travels. These velocities can differ, especially in dispersive media where wave speed depends on frequency. Classical wave theory provides a comprehensive framework for understanding a wide range of physical phenomena. Its principles are fundamental to many areas of science and engineering, offering insights into the behavior of waves and their interactions with matter and energy. This theory continues to be a cornerstone of physics, underpinning our understanding of the natural world. Classical physics, while immensely successful in describing many natural phenomena, has significant limitations. These limitations became evident with the advent of new experimental discoveries in the late 19th and early 20th centuries. Understanding these limitations is crucial for appreciating the development of modern physics. One major limitation of classical physics is its inability to explain the behavior of matter and energy at very small scales, such as those of atoms and subatomic particles. The classical models could not account for the discrete nature of energy levels observed in atomic spectra, leading to the development of quantum mechanics. Another significant limitation is in explaining phenomena involving very high speeds, close to the speed of light. Classical mechanics assumes that time and space are absolute and invariant, which contradicts the results of experiments involving fast-moving objects. This discrepancy led to the development of Einstein's theory of relativity. Classical physics also fails to accurately describe the behavior of light and other electromagnetic radiation. The wave theory of light could not explain the photoelectric effect, where light incident on a material ejects electrons. This phenomenon required a quantum explanation, introducing the concept of photons. The concept of absolute space and time in Newtonian mechanics was challenged by the theory of relativity. Einstein's special relativity demonstrated that time and space are relative and interconnected, fundamentally altering our understanding of these concepts and showing that the laws of physics are the same for all non-accelerating observers. General relativity further revealed the limitations of classical physics in explaining gravity. Newton's law of gravitation, while effective for most purposes, could not account for the precise motion of planets and the bending of light by gravity. General relativity provided a more comprehensive framework by describing gravity as the curvature of space-time. Classical thermodynamics faced limitations when dealing with the microscopic behavior of particles. It could not explain phenomena like Brownian motion or the specific heat capacities of gases at low temperatures. These issues were resolved by statistical mechanics, which applies quantum principles to thermodynamic systems. The classical theory of electromagnetism, encapsulated in Maxwell's equations, does not account for quantum effects in electromagnetic interactions. Quantum electrodynamics, QED, extends classical electromagnetism to include quantum phenomena, providing more accurate predictions and explanations for the behavior of light and matter. Classical wave theory, while successful in describing many wave phenomena, cannot explain the dual nature of particles and waves observed in quantum mechanics. Experiments like the double-slit experiment reveal that particles exhibit both wave-like and particle-like properties, necessitating a quantum description. Classical physics is also inadequate in describing systems at extremely low temperatures. Phenomena like superconductivity, where materials conduct electricity without resistance, cannot be explained by classical theories. Quantum mechanics and condensed matter physics provide the necessary frameworks to understand these effects. The deterministic nature of classical physics, where the future behavior of a system can be precisely predicted given its initial conditions, is contradicted by the inherent uncertainty in quantum mechanics. Heisenberg's uncertainty principle states that certain pairs of physical properties cannot be simultaneously known to arbitrary precision. Classical physics does not incorporate the concept of quantum entanglement, where particles become correlated in ways that classical theories cannot explain. Entanglement plays a crucial role in quantum computing and quantum information theory, areas beyond the scope of classical understanding. In the realm of cosmology, classical physics fails to explain the behavior of the universe at its largest scales. Dark matter and dark energy, which constitute most of the universe's mass-energy content, have no place in classical theories. Modern cosmological models rely on both general relativity and quantum field theories. The classical theory of gases, based on the ideal gas law, cannot account for real-world deviations observed at high pressures and low temperatures. Real gas behavior is better explained by quantum statistics and intermolecular forces, which classical physics does not consider. Classical physics also struggles with the concept of black body radiation, the emission of electromagnetic radiation by a perfect absorber. Classical theories predicted an ultraviolet catastrophe, where energy radiated at high frequencies becomes infinite. Quantum mechanics resolved this with Planck's law, introducing the concept of quantized energy levels. These limitations of classical physics highlight the necessity for new theories and models to accurately describe the natural world. The development of quantum mechanics, relativity, and other modern theories has significantly expanded our understanding, providing a more complete and nuanced picture of the universe. Special relativity, formulated by Albert Einstein in 1905, revolutionized our understanding of space, time, and motion. It emerged from the need to reconcile the laws of electromagnetism with the principles of mechanics, leading to profound changes in our view of the universe. At the heart of special relativity is the idea that the laws of physics are the same for all observers in uniform motion, regardless of their relative velocity. This principle is known as the principle of relativity, and it applies to all physical phenomena, not just mechanics. Another key postulate of special relativity is that the speed of light in a vacuum is constant and independent of the motion of the light source or the observer. This invariance of the speed of light challenged the classical notions of absolute time and space. One of the most famous consequences of special relativity is time dilation. It states that time passes more slowly for an observer in motion relative to a stationary observer. This effect becomes significant at speeds approaching the speed of light, dramatically altering our perception of time. Length contraction is another striking result of special relativity. It predicts that objects in motion contract along the direction of motion as their speed approaches the speed of light. This contraction is imperceptible at everyday speeds but becomes noticeable at relativistic velocities. Special relativity also introduced the concept of simultaneity. According to this theory, events that are simultaneous for one observer may not be simultaneous for another observer moving at a different velocity. This relative nature of simultaneity fundamentally changes our understanding of time. The famous equation E equals mc2 emerges from special relativity, showing the equivalence of mass and energy. This equation implies that a small amount of mass can be converted into a large amount of energy, a principle that underlies nuclear reactions and has profound implications for both physics and energy generation. Special relativity affects the dynamics of particles moving at high velocities. It modifies the classical equations of motion, leading to relativistic momentum and energy, which increase dramatically as an object's speed approaches the speed of light. The theory also has implications for electromagnetism. Maxwell's equations, which describe the behavior of electric and magnetic fields, are consistent with special relativity. This consistency helped validate Einstein's theory and demonstrated its broad applicability. Special relativity resolved the long-standing issue of the Michelson-Morley experiment, which failed to detect any variation in the speed of light due to Earth's motion through the supposed ether. Einstein's theory eliminated the need for the ether, showing that the speed of light is constant in all inertial frames. The concept of spacetime, a four-dimensional continuum combining 3 dimensions of space and 1 of time, arises naturally from special relativity. This unified framework replaces the separate notions of space and time, providing a more comprehensive understanding of the universe's structure. Special relativity has practical applications in modern technology. Global positioning systems, GPS, for example, must account for time dilation effects due to the relative motion of satellites and observers on Earth to provide accurate location data. Particle accelerators, which propel particles to speeds close to the speed of light, rely on the principles of special relativity to design and interpret experiments. These high-energy experiments provide insights into the fundamental particles and forces of nature. The theory also plays a crucial role in the development of quantum field theory, which combines quantum mechanics and special relativity. This combination is essential for understanding the behavior of particles at high energies, and has led to the development of the standard model of particle physics. Special relativity's impact extends beyond physics, influencing philosophy and our understanding of reality. It challenges intuitive notions of space and time, forcing us to reconsider the nature of the universe and our place within it. This profound shift in perspective continues to inspire and shape scientific thought. General relativity, introduced by Albert Einstein in 1915, extended the principles of special relativity to include gravity. This theory provides a new understanding of gravity as a geometric property of space and time, or spacetime. At the core of general relativity is the idea that massive objects cause spacetime to curve, and this curvature affects the motion of objects. This replaces the Newtonian concept of gravity as a force between masses. The famous equation of general relativity, the Einstein field equations, describe how matter and energy influence the curvature of spacetime. These equations are complex and show that the presence of mass and energy determines the geometry of the surrounding spacetime. One of the key predictions of general relativity is the bending of light by gravity. This effect, known as gravitational lensing, occurs when light passes near a massive object, causing the light to bend. This phenomenon has been observed in astronomical observations, confirming the theory's predictions. General relativity also predicts the existence of black holes, regions of spacetime where gravity is so strong that not even light can escape. Black holes are formed when massive stars collapse under their own gravity, and their existence has been confirmed through various astronomical observations. Another significant prediction is the expansion of the universe. General relativity allows for dynamic solutions where the universe can expand or contract. Observations of distant galaxies show that the universe is expanding, a discovery that led to the development of the Big Bang theory. The theory also predicts the existence of gravitational waves, ripples in the fabric of spacetime caused by accelerating massive objects. These waves were directly detected for the first time in 2015 by the LIGO Observatory, providing further confirmation of general relativity. General relativity has profound implications for our understanding of time. In the presence of strong gravitational fields, time passes more slowly, a phenomenon known as gravitational time dilation. This effect has been confirmed by experiments with atomic clocks placed at different altitudes. The theory also plays a crucial role in modern cosmology. It provides the framework for understanding the large-scale structure of the universe, the formation of galaxies, and the behavior of cosmic objects under extreme conditions. General relativity challenges our intuitive notions of space and time, showing that they are interconnected and dynamic. This has led to new ways of thinking about the universe and our place within it, influencing both science and philosophy. The mathematical complexity of general relativity makes it a challenging field of study. However, its predictions have been confirmed by numerous experiments and observations, solidifying its status as a cornerstone of modern physics. The GPS system relies on corrections from general relativity to provide accurate positioning data. The difference in the passage of time between satellites and the Earth's surface must be accounted for. illustrating the practical applications of the theory. General relativity has also led to new questions and areas of research, such as the nature of dark matter and dark energy. These mysterious components of the universe influence its expansion and structure, but are not yet fully understood. The theory continues to inspire and challenge physicists, leading to ongoing research and new discoveries. It remains one of the most profound and far-reaching theories in science, shaping our understanding of the universe. As we explore the universe, from the smallest particles to the largest cosmic structures, general relativity provides the framework for making sense of our observations. Its legacy is a testament to the power of human curiosity and the quest for knowledge. The concept of the space-time continuum is central to both special and general relativity. It combines the three dimensions of space with the fourth dimension of time into a single four-dimensional framework. This unification allows us to describe the physical universe more comprehensively. In the space-time continuum, events are described by 4 coordinates, 3 spatial coordinates, and 1 time coordinate. This framework helps explain how the positions and times of events are interconnected, providing a more accurate description of reality. The idea of the space-time continuum challenges the notion of absolute space and time, which were fundamental to Newtonian physics. Instead, the measurements of space and time are relative, depending on the observer's state of motion. In special relativity, the space-time continuum is flat, meaning that the geometry of space-time is not influenced by mass or energy. However, the theory still predicts phenomena like time dilation and length contraction, which result from the relative motion of observers. General relativity extends this concept by introducing curvature to the space-time continuum. Massive objects cause space-time to curve, and this curvature affects the motion of objects and light, providing a new understanding of gravity. The curvature of space-time is described mathematically by the Einstein field equations. These equations show how matter and energy influence the shape of space-time, leading to phenomena such as the bending of light and the orbits of planets. A significant implication of the space-time continuum is the idea of geodesics. In curved space-time, objects move along paths called geodesics, which are the closest analog to straight lines in curved space. These paths determine the natural motion of objects under the influence of gravity. Black holes are an extreme example of the curvature of space-time. In the vicinity of a black hole, space-time is so strongly curved that nothing, not even light, can escape. The event horizon marks the boundary beyond which escape is impossible. The concept of the space-time continuum also leads to the idea of space-time diagrams. These diagrams graphically represent events in space-time, allowing us to visualize the effects of relative motion and gravitational fields on space and time. In cosmology, the space-time continuum helps describe the large-scale structure of the universe. The expansion of the universe can be understood as the stretching of space-time, where galaxies move apart as space itself expands. Gravitational waves are ripples in the space-time continuum, caused by accelerating masses, such as colliding black holes. The detection of these waves has opened a new way of observing the universe, providing insights into violent cosmic events. The space-time continuum also affects time travel concepts. While general relativity permits solutions that suggest the possibility of time travel, such as wormholes, these remain speculative and face significant theoretical and practical challenges. In quantum mechanics, integrating the space-time continuum with quantum principles is an ongoing challenge. The quest for a quantum theory of gravity seeks to reconcile the continuous nature of space-time with the discrete nature of quantum mechanics. The space-time continuum fundamentally changes our understanding of cause and effect. In this framework, the ordering of events can differ between observers in relative motion, highlighting the intricate relationship between space and time. Overall, the concept of the space-time continuum provides a unified framework for understanding the universe's structure and dynamics. It is a profound and far-reaching idea that continues to shape our exploration of the cosmos. Gravitational waves are ripples in the fabric of space-time caused by the acceleration of massive objects. Predicted by Albert Einstein in his theory of general relativity, these waves travel at the speed of light, carrying energy away from their sources. The concept of gravitational waves arises from the idea that space-time is not static, but can be disturbed by the movements of mass. When massive objects like black holes or neutron stars move or collide, they generate waves that propagate outward through space-time. Gravitational waves were first indirectly detected by observing the behavior of binary pulsars. These systems consist of two neutron stars orbiting each other, gradually losing energy and spiraling closer together. This energy loss matched the predictions made by general relativity, suggesting that it was due to the emission of gravitational waves. The direct detection of gravitational waves was achieved in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO. This groundbreaking discovery confirmed the existence of gravitational waves and opened a new era in astronomy and astrophysics. LIGO detects gravitational waves using laser interferometry. Two long arms, set at right angles, measure minor changes in length caused by passing gravitational waves. The incredibly small changes in distance are measured with extreme precision, allowing scientists to detect waves from distant cosmic events. Gravitational waves provide a new way of observing the universe, complementary to traditional electromagnetic observations. They carry information about their sources, such as the masses, spins, and orbital dynamics of merging black holes or neutron stars, which cannot be obtained from light alone. One of the most significant discoveries made possible by gravitational wave detection was the observation of a binary neutron star merger. This event, detected by LIGO and Virgo in 2017, was accompanied by electromagnetic signals observed across the spectrum, providing a wealth of information about the processes involved in such mergers. Gravitational waves can also offer insights into the fundamental nature of gravity and spacetime. By studying these waves, scientists can test the predictions of general relativity and the strong field regime, where gravitational forces are extremely intense, and explore potential deviations from the theory. The study of gravitational waves has led to the development of multi-messenger astronomy, where gravitational wave observations are combined with electromagnetic and neutrino detections. This approach provides a more comprehensive understanding of cosmic events, revealing details that would be missed by observing only one type of signal. Future gravitational wave detectors, such as the space-based LISA mission, will enhance our ability to detect these waves from a broader range of sources. LISA will be sensitive to lower-frequency gravitational waves, enabling the study of supermassive black hole mergers and other phenomena inaccessible to ground-based detectors. Gravitational waves also offer the potential to probe the early universe, possibly detecting signals from the inflationary period shortly after the Big Bang. These primordial gravitational waves would provide direct evidence of the universe's rapid expansion and offer clues about its origin and evolution. The detection of gravitational waves has already led to several Nobel Prizes in physics, highlighting the significance of this discovery. The pioneering work of scientists and engineers in developing the technology to detect these waves has revolutionized our understanding of the universe. As the field of gravitational wave astronomy continues to grow, it promises to reveal more about the most violent and energetic processes in the cosmos. Each new detection provides valuable data, contributing to our knowledge of black holes, neutron stars, and other exotic objects. Gravitational wave observations also have implications for fundamental physics, potentially offering insights into quantum gravity and the unification of general relativity with quantum mechanics. These waves provide a unique testing ground for theories that aim to reconcile these two foundational pillars of physics. The study of gravitational waves exemplifies the synergy between theoretical predictions and experimental breakthroughs. It shows how persistent efforts to test and expand our understanding of the universe can lead to profound discoveries, reshaping our view of the cosmos and our place within it. The impact of these discoveries on modern physics cannot be overstated. Gravitational waves have fundamentally changed how we observe and understand the universe. By providing a new way to look at cosmic events, they have enriched our knowledge and opened up previously inaccessible areas of research. These waves allow us to study black holes in unprecedented detail. We can now observe the dynamics of black hole mergers, understanding their properties and behavior in ways that were previously impossible. This has confirmed many predictions of general relativity and provided new insights into the nature of these enigmatic objects. Gravitational wave astronomy has also enhanced our understanding of neutron stars. Observations of neutron star mergers have revealed information about their structure, composition, and the extreme physical conditions inside them. These findings are crucial for studying matter under the most extreme pressures and densities. The detection of gravitational waves has led to significant advancements in technology and instrumentation. The precision required to measure these waves has driven innovations in laser interferometry, vibration isolation, and data analysis techniques. These technological advancements have applications beyond gravitational wave detection, influencing other areas of science and engineering. The study of gravitational waves has also impacted our understanding of cosmology. By observing the waves from distant cosmic events, we can learn more about the history and evolution of the universe. This includes insights into the rate of expansion of the universe and the properties of dark matter and dark energy. The confirmation of gravitational waves has strengthened the case for general relativity as the correct description of gravity. However, it has also highlighted areas where our understanding is incomplete, prompting further research into quantum gravity and the potential unification of general relativity with quantum mechanics. Gravitational waves have introduced new methods for testing fundamental physics. By comparing the observed waveforms with theoretical predictions, we can test the limits of general relativity and search for deviations that might indicate new physics. This has implications for understanding the fundamental forces of nature. The interdisciplinary nature of gravitational wave research has fostered collaboration between different fields of science. Astrophysicists, cosmologists, particle physicists, and engineers work together to analyze data and interpret findings. This collaborative approach has led to a more integrated understanding of the universe. Gravitational waves have also influenced the field of quantum mechanics. The detection and analysis of these waves involve quantum technologies and concepts, bridging the gap between macroscopic astronomical phenomena and microscopic quantum processes. This interplay is crucial for developing a unified theory of physics. The discoveries made possible by gravitational waves have inspired new generations of scientists. The excitement and potential of this field have drawn many young researchers to study physics, astronomy, and engineering. This influx of talent is vital for the continued advancement of science. The impact on education has been profound. Gravitational wave astronomy is now a key topic in physics curricula from high school to university. It serves as a powerful example of how theoretical predictions can be confirmed through experimentation and observation, illustrating the scientific method in action. The public interest in gravitational waves has increased awareness and appreciation of science. Major discoveries have been widely reported in the media, capturing the imagination of people around the world. This has led to greater support for scientific research and funding. Gravitational waves have broadened our perspective on the universe. They provide a new way to observe and understand the cosmos, complementing traditional methods based on electromagnetic radiation. This multi-messenger approach is essential for a comprehensive understanding of astronomical phenomena. The future of gravitational wave research is promising. Upcoming detectors and observatories will be more sensitive, capable of detecting weaker and more distant signals. This will expand our observational reach, allowing us to study a wider variety of cosmic events and objects. Ultimately, the discovery and study of gravitational waves have transformed modern physics. They have provided new tools, confirmed fundamental theories, and opened up exciting avenues for future research. As we continue to explore this new frontier, our understanding of the universe will undoubtedly deepen, leading to further groundbreaking discoveries. Quantum theory, or quantum mechanics, is the branch of physics that deals with the behavior of particles on the smallest scales. It was developed in the early 20th century to explain phenomena that classical physics could not. At the heart of quantum theory is the concept of quantization. Energy, momentum, and other quantities are not continuous, but come in discrete units called quanta. This idea was first introduced by Max Planck to explain black body radiation. The wave-particle duality is a fundamental principle of quantum theory. It states that particles, such as electrons and photons, exhibit both wave-like and particle-like properties. This duality is evident in experiments like the double-slit experiment, where particles create an interference pattern characteristic of waves. Heisenberg's uncertainty principle is another cornerstone of quantum mechanics. It asserts that certain pairs of properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. The more precisely one property is known, the less precisely the other can be known. The principle of superposition is crucial to understanding quantum systems. A quantum system can exist in multiple states simultaneously until it is measured. Upon measurement, the system collapses into one of the possible states, a phenomenon known as wave function collapse. Quantum entanglement is a remarkable feature of quantum mechanics. When particles become entangled, the state of one particle is instantly correlated with the state of another, regardless of the distance between them. This phenomenon has been experimentally verified and challenges classical notions of locality. The Schrödinger equation is the fundamental equation of quantum mechanics. It describes how the wave function of a quantum system evolves over time. The wave function contains all the information about the system's state and allows the calculation of probabilities for different outcomes. Probability and randomness are inherent in quantum mechanics. Unlike classical physics, which predicts definite outcomes, quantum mechanics provides only probabilities for different outcomes. This probabilistic nature is a fundamental aspect of the theory. Quantum tunneling is a phenomenon where particles can pass through barriers that would be insurmountable according to classical physics. This effect is essential for many processes, including nuclear fusion in stars and the operation of certain electronic devices. The concept of spin is unique to quantum mechanics. Spin is an intrinsic form of angular momentum carried by particles, which does not have a classical counterpart. Particles like electrons and photons have specific spin values that play crucial roles in their behavior and interactions. Quantum mechanics also introduces the concept of wave functions for particles. These wave functions describe the probability distributions of particles' positions and momenta. The square of the wave function's amplitude gives the probability density of finding a particle in a particular state. The Pauli exclusion principle states that no two fermions, such as electrons, can occupy the same quantum state simultaneously. This principle explains the structure of the periodic table and the stability of matter, as it prevents electrons from collapsing into the same state. Quantum field theory extends quantum mechanics to fields, describing how particles are excitations of underlying fields. This framework successfully explains the interactions of particles and is the basis for the standard model of particle physics. The concept of decoherence explains how classical behavior emerges from quantum systems. It describes the process by which a quantum system loses its quantum coherence due to interactions with its environment, resulting in classical probabilities instead of quantum superpositions. Quantum mechanics has led to numerous technological advancements. Technologies such as lasers, transistors, and quantum computers are all based on principles of quantum mechanics. The theory continues to drive innovation and deepen our understanding of the fundamental nature of reality. Wave-particle duality is a fundamental concept in quantum mechanics that describes how particles such as electrons and photons exhibit both wave-like and particle-like properties. This duality is at the heart of understanding the behavior of quantum systems. The idea of wave-particle duality emerged from experiments that showed light behaves as both a wave and a particle. Thomas Young's double-slit experiment in the early 19th century demonstrated that light produces an interference pattern, a hallmark of wave behavior. However, the photoelectric effect, explained by Albert Einstein in 1905, showed that light can also be thought of as particles called photons. In this effect, light striking a metal surface ejects electrons, a phenomenon that could not be explained by wave theory alone. In quantum mechanics, particles such as electrons also exhibit wave-like properties. When electrons pass through a double slit, they create an interference pattern similar to that produced by light waves, indicating their wave nature. The de Broglie hypothesis, proposed by Louis de Broglie in 1924, extended the concept of wave-particle duality to all matter. He suggested that every particle has an associated wave, with a wavelength inversely proportional to its momentum. This idea was later confirmed by experiments with electrons and other particles. Wave-particle duality challenges our classical understanding of physics. In classical physics, waves and particles are distinct entities. Waves are continuous and spread out, while particles are discrete and localized. Quantum mechanics reveals that this distinction is not always clear-cut. The principle of complementarity, introduced by Niels Bohr, states that wave and particle aspects are complementary properties of quantum objects. Depending on the experimental setup, Either the wave-like or particle-like behavior can be observed, but not both simultaneously. This duality is central to the interpretation of quantum mechanics. The wave function, which describes the quantum state of a system, incorporates both wave and particle characteristics. The probability of finding a particle in a particular location is given by the square of the wave function's amplitude. Interference and diffraction are key phenomena that illustrate wave-particle duality. When particles such as electrons pass through a double slit, they interfere with themselves, creating a pattern of constructive and destructive interference. This behavior is similar to that of waves passing through slits. Wave-particle duality also plays a crucial role in the uncertainty principle. The wave-like nature of particles means that their position and momentum cannot be precisely known simultaneously. The more accurately one property is measured, the less accurately the other can be determined. In experiments with single particles, wave-particle duality is evident. When a single electron or photon is sent through a double slit, it behaves as a particle, creating a single impact on a detector. But when many such impacts are recorded, they form an interference pattern, revealing the wave nature of the particles. Quantum superposition is another consequence of wave-particle duality. A quantum system can exist in multiple states simultaneously, represented by a wave function that combines these states. Measurement causes the wave function to collapse to a single state, reflecting the particle aspect. Wave-particle duality has practical implications for technology. Electron microscopy, for instance, relies on the wave nature of electrons to achieve high-resolution images. Quantum computing and other advanced technologies also exploit the duality of quantum systems. The concept of wave-particle duality continues to inspire and challenge physicists. It defies our classical intuitions and highlights the richness and complexity of the quantum world. Understanding and harnessing this duality is key to advancing both fundamental science and practical applications. Wave-particle duality underscores the need for a new way of thinking about nature. It reveals the limitations of classical concepts and opens up a realm of possibilities that are only beginning to be explored. As we continue to investigate the quantum world, wave-particle duality remains a central and fascinating principle. The Heisenberg uncertainty principle is a fundamental concept in quantum mechanics, introduced by Werner Heisenberg in 1927. It states that certain pairs of physical properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. According to the uncertainty principle, the more accurately we know the position of a particle, the less accurately we can know its momentum, and vice versa. This intrinsic limitation is not due to measurement imperfections, but is a fundamental feature of quantum systems. Mathematically, the uncertainty principle is expressed by the inequality dx dp-h2, where dx is the uncertainty in position, dp is the uncertainty in momentum, and h is the reduced Planck constant. This inequality quantifies the trade-off between the uncertainties of these properties. The uncertainty principle arises from the wave-like nature of particles in quantum mechanics. Since particles exhibit wave properties, their position and momentum are described by wave functions. The spread of the wave function in space determines the uncertainty in position, while its spread in momentum space determines the uncertainty in momentum. This principle challenges our classical intuition, where it is possible to measure both position and momentum precisely. In the quantum realm, however, the wave-particle duality implies that these quantities are fundamentally intertwined, leading to inherent limitations in our knowledge. The uncertainty principle has profound implications for the behavior of quantum systems. It implies that particles do not have definite trajectories, as they would in classical mechanics. Instead, their motion is described by probabilities and wave functions. In quantum mechanics, the act of measurement affects the system being measured. When we measure the position of a particle, we disturb its momentum, and vice versa. This measurement disturbance is a key aspect of the uncertainty principle and highlights the active role of the observer in quantum theory. The uncertainty principle also applies to other pairs of complementary properties, such as energy and time. The energy-time uncertainty relation states that the uncertainty in energy and the uncertainty in time are inversely related, with the product of these uncertainties being on the order of h. This principle is crucial for understanding various quantum phenomena, such as the stability of atoms. The uncertainty in the position of an electron within an atom, combined with the uncertainty in its momentum, prevents the electron from spiraling into the nucleus, thus ensuring the stability of atomic structures. The uncertainty principle also has implications for quantum field theory and particle physics. It sets limits on the precision with which we can measure the properties of particles and fields, influencing the design and interpretation of high-energy experiments. In the context of quantum computing, the uncertainty principle affects the behavior of quantum bits or qubits. Qubits can exist in superpositions of states, but the uncertainty principle limits the precision with which their states can be controlled and measured. The uncertainty principle plays a role in the interpretation of quantum mechanics. Different interpretations, such as the Copenhagen interpretation and the many worlds interpretation, offer various perspectives on the nature of uncertainty and measurement in quantum systems. Experimental evidence supports the uncertainty principle. Numerous experiments, including those involving electron diffraction and quantum optics, have confirmed the fundamental limits on simultaneous measurements of complementary properties. The uncertainty principle is also related to the concept of quantum entanglement. When particles become entangled, the measurement of one particle instantaneously affects the state of the other, regardless of the distance between them. This non-local correlation is consistent with the limitations imposed by the uncertainty principle. Understanding the Heisenberg uncertainty principle is essential for grasping the nature of the quantum world. It reveals the inherent limitations of our knowledge and challenges us to rethink classical concepts of measurement and determinism. The Heisenberg uncertainty principle remains a cornerstone of quantum mechanics, providing deep insights into the nature of reality. It underscores the probabilistic nature of quantum theory and continues to inspire new research and technological advancements in the field. Quantum entanglement is one of the most intriguing and counterintuitive phenomena in quantum mechanics. It occurs when particles become so deeply linked that the state of one particle instantaneously influences the state of another, no matter how far apart they are. This phenomenon was first described by Albert Einstein, Boris Podolsky, and Nathan Rosen in a paper in 1935. They highlighted the strange nature of entanglement, referring to it as spooky action at a distance. Einstein was particularly troubled by the idea, as it seemed to contradict the principle of locality. Entanglement occurs when particles interact in such a way that their quantum states become inseparable. This means that the state of each particle cannot be described independently of the state of the other particle. Instead, the system must be described as a whole. When particles are entangled, measuring the state of one particle instantly determines the state of the other. For example, if two particles are entangled in such a way that their spins are opposite, measuring the spin of one particle immediately tells us the spin of the other, regardless of the distance between them. This instantaneous connection between entangled particles appears to violate the principle that information cannot travel faster than the speed of light. However, no information is actually transmitted between the particles in a way that would allow faster-than-light communication, preserving the theory of relativity. Entanglement has been experimentally confirmed through numerous tests of Bell's theorem. These experiments demonstrate that the predictions of quantum mechanics cannot be reproduced by any local hidden variable theory, strongly supporting the reality of entanglement. Quantum entanglement is not just a theoretical curiosity. It has practical applications in the field of quantum information science. Entanglement is a key resource for quantum computing, quantum cryptography, and quantum teleportation. In quantum computing, entangled qubits can perform complex calculations much faster than classical bits. Entanglement allows quantum computers to process information in parallel, vastly increasing their computational power for certain tasks. Quantum cryptography uses entanglement to create secure communication channels. By entangling particles and distributing them to different parties, any attempt to eavesdrop on the communication can be detected, ensuring the security of the transmitted information. Quantum teleportation, enabled by entanglement, allows the transfer of quantum states from one location to another without moving the physical particles themselves. This process involves entangling particles, performing a measurement on one particle, and using the result to instantaneously affect the state of the distant particle. The study of entanglement has also led to the development of quantum networks, where entangled particles can be used to transmit information across large distances. These networks have the potential to revolutionize communication and computation by creating a global quantum internet. Entanglement challenges our understanding of reality and locality. It suggests that particles can be connected in ways that transcend classical concepts of space and time, implying a deeper level of interconnectedness in the universe. The phenomenon of entanglement has inspired various interpretations of quantum mechanics. The Copenhagen interpretation views entanglement as a fundamental aspect of quantum measurement, while the many worlds interpretation suggests that entangled particles exist in multiple parallel universes. Entanglement also plays a crucial role in understanding quantum decoherence, the process by which quantum systems interact with their environment and lose their quantum coherence. This process explains how classical behavior emerges from quantum systems. Research into quantum entanglement continues to advance our knowledge of quantum mechanics and its applications. New experiments and theoretical developments are constantly expanding our understanding of this mysterious and powerful phenomenon. Quantum entanglement remains a central and fascinating topic in physics, highlighting the profound and often surprising nature of the quantum world. Its study continues to push the boundaries of science and technology, revealing new insights into the fundamental workings of the universe. Quantum field theory, or QFT, is the framework that combines quantum mechanics with special relativity to describe the behavior of fields and particles. It is the foundation for understanding the interactions of elementary particles in modern physics. In QFT, particles are seen as excitations of underlying fields that permeate all of space. For instance, the electron is an excitation of the electron field, and the photon is an excitation of the electromagnetic field. This perspective unifies particles and fields into a single framework. The formulation of QFT begins with the quantization of classical fields. This process involves applying the principles of quantum mechanics to fields, leading to the creation and annihilation of particles. These particles are described by operators that act on the quantum state of the field. One of the key concepts in QFT is the Lagrangian, which encapsulates the dynamics of the field. The Lagrangian density is a function that, when integrated over space and time, gives the action. The equations of motion for the fields are derived by finding the stationary points of the action. Feynman diagrams are a powerful tool used in QFT to visualize and calculate interactions between particles. These diagrams represent the paths taken by particles as they exchange force carriers, such as photons or gluons. Each diagram corresponds to a term in the perturbation expansion of the interaction probability. Renormalization is an essential technique in QFT that deals with infinities arising in calculations. By systematically absorbing these infinities into a few measurable quantities, such as mass and charge, QFT provides finite and physically meaningful results. This process ensures that predictions match experimental observations. The standard model of particle physics is a triumph of QFT, describing the electromagnetic, weak and strong nuclear interactions. It incorporates three fundamental forces and all known elementary particles except gravity. The Higgs mechanism within the standard model explains how particles acquire mass. Quantum electrodynamics, or QED, is the QFT of the electromagnetic force. It describes the interactions between charged particles and photons with extraordinary precision. QED has been tested extensively, with its predictions matching experimental results to an extremely high degree of accuracy. Quantum chromodynamics, or QCD, is the QFT of the strong nuclear force. It describes the interactions between quarks and gluons, which make up protons, neutrons, and other hadrons. QCD explains phenomena such as confinement, where quarks are never found in isolation, and asymptotic freedom, where quarks interact more weakly at high energies. The electroweak theory unifies the electromagnetic and weak nuclear forces into a single theoretical framework. This unification was achieved by Sheldon Glashow, Abdus Salam, and Steven Weinberg, who showed that these two forces are different manifestations of a single electroweak force at high energies. QFT also plays a crucial role in understanding spontaneous symmetry breaking, where a system that is symmetric under certain transformations ends up in an asymmetric state. The Higgs boson, discovered in 2012, is a key example of this phenomenon, providing evidence for the mechanism that gives particles mass. In addition to the standard model, QFT has applications in condensed matter physics. It helps explain the behavior of many body systems, phase transitions, and phenomena such as superconductivity and the quantum Hall effect. These applications show the versatility and power of QFT beyond particle physics. The quest to include gravity in QFT leads to the idea of quantum gravity. While a complete theory of quantum gravity remains elusive, approaches such as string theory and loop quantum gravity aim to reconcile the principles of QFT with general relativity. This endeavor seeks to unify all fundamental forces into a single coherent framework. Quantum field theory has revolutionized our understanding of the fundamental forces and particles. It provides the mathematical and conceptual tools to explore the universe at its most basic level, leading to profound insights and groundbreaking discoveries. The development and refinement of QFT continue to be at the forefront of theoretical physics. It remains an essential framework for interpreting experimental data, guiding new research, and expanding our comprehension of the natural world. As we delve deeper into the mysteries of the universe, QFT will undoubtedly play a central role in our journey. The universe is governed by four fundamental forces that dictate the interactions between particles. These forces are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each plays a crucial role in shaping the behavior of matter and the structure of the cosmos. Gravity is the force of attraction between masses. It governs the motion of planets, stars, galaxies, and even light. Although it is the weakest of the four forces, its influence is far-reaching due to its infinite range. Gravity is described by Einstein's general theory of relativity as the curvature of space-time caused by mass and energy. Electromagnetism is the force between charged particles. It operates over an infinite range and is responsible for phenomena such as light, electricity, and magnetism. Electromagnetism is described by Maxwell's equations and quantum electrodynamics, which unify electric and magnetic fields into a single theoretical framework. The strong nuclear force is the force that binds quarks together to form protons and neutrons and holds the atomic nucleus together. It is the strongest of the four forces but operates only over very short distances, on the order of a femtometer. Quantum chromodynamics, or QCD, describes the interactions of the strong force through the exchange of gluons between quarks. The weak nuclear force is responsible for processes such as beta decay in radioactive atoms. It has a very short range, much less than the diameter of a proton, and is mediated by the exchange of W and Z bosons. The weak force plays a crucial role in the nuclear fusion processes that power stars. Each of these fundamental forces has a corresponding force carrier particle. Photons mediate the electromagnetic force. Gluons mediate the strong force. W and Z bosons mediate the weak force. And the hypothetical graviton is thought to mediate gravity. These particles are all part of the standard model of particle physics, except the graviton, which remains theoretical. The electromagnetic and weak forces were unified into the electroweak theory in the 1970s. This unification showed that at high energies, these two forces become indistinguishable, hinting at a deeper connection between them. The success of the electroweak theory was confirmed by the discovery of the W and Z bosons in the 1980s. The quest for a grand unified theory, or GUT, aims to unify the strong, weak, and electromagnetic forces into a single theoretical framework. While several candidate theories exist, experimental confirmation remains elusive. GUTs predict that at extremely high energies, all three forces merge into one. Gravity's unification with the other three forces is one of the biggest challenges in theoretical physics. String theory is a leading candidate for such unification, proposing that particles are not point-like, but rather tiny, vibrating strings. This theory suggests that all fundamental forces and particles arise from different vibrational states of these strings. Another approach to unifying gravity with the other forces is loop quantum gravity. This theory attempts to quantize space-time itself, suggesting that space and time are composed of discrete loops. While promising, loop quantum gravity has yet to achieve the same level of experimental support as other theories. The interplay between these fundamental forces shapes the universe at every level. Gravity governs the large-scale structure of the cosmos, forming galaxies, stars, and planets. Electromagnetism dominates the interactions between atoms and molecules, enabling chemistry and biology. The strong force is crucial for the stability of atomic nuclei, without which matter as we know it could not exist. The weak force drives the nuclear reactions in stars, producing the elements necessary for life. Understanding these forces helps us comprehend the fundamental workings of the universe. Experimental research continues to probe the nature of these forces, using particle accelerators like the Large Hadron Collider to explore the high-energy conditions where unification might occur. Observations of the cosmos, from gravitational waves to cosmic microwave background radiation, also provide crucial insights. The discovery of the Higgs boson in 2012 was a major milestone, confirming the mechanism that gives particles mass and further validating the Standard Model. However, many questions remain, such as the nature of dark matter and dark energy, which are not yet fully understood within the current framework. As we continue to explore the fundamental forces, we push the boundaries of human knowledge. Each discovery brings us closer to a more unified and complete understanding of the universe. The quest to understand these forces is not just a pursuit of knowledge, but a journey to uncover the deepest truths of nature. The Standard Model of particle physics is a theoretical framework that describes the fundamental particles and their interactions. It is the culmination of decades of experimental and theoretical work, and stands as one of the most successful theories in science. At the core of the Standard Model are the fundamental particles, which are divided into two categories, quarks and leptons. There are 6 types of quarks: up, down, charm, strange, top, and bottom. Similarly, there are 6 types of leptons: electron, muon, tau, and their corresponding neutrinos. These particles interact through 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Gravity is not included in the Standard Model, as it is described by general relativity, a separate framework. The electromagnetic force is mediated by photons, the quantum of light. The weak nuclear force is mediated by W and Z bosons, which are massive particles responsible for processes like beta decay. The strong nuclear force is mediated by gluons, which bind quarks together inside protons and neutrons. The Standard Model also includes the Higgs boson, discovered in 2012 at the Large Hadron Collider. The Higgs boson is associated with the Higgs field, which gives mass to other particles through the mechanism of spontaneous symmetry breaking. Each particle in the Standard Model has a corresponding antiparticle with the same mass but opposite charge. When particles and antiparticles meet, they annihilate each other, producing energy. This symmetry between particles and antiparticles is a fundamental aspect of the theory. The interactions of particles are described by quantum field theories, which use mathematical constructs known as fields to represent the particles. The dynamics of these fields are governed by the Standard Model's Lagrangian, a function that encapsulates all the forces and particles' behaviors. Renormalization is a key technique in the Standard Model, dealing with infinities that arise in calculations. By redefining certain parameters, physicists can make meaningful, finite predictions that match experimental data with high precision. The discovery of the Higgs boson was a significant milestone, confirming the last missing piece of the Standard Model. Its existence and properties were predicted by the theory, and its discovery provided crucial evidence for the mechanism that gives particles mass. Despite its successes, the Standard Model is not complete. It does not include gravity, nor does it explain dark matter and dark energy, which constitute most of the universe's mass and energy. Additionally, the masses of neutrinos, which are incredibly light, are not fully explained by the Standard Model. Extensions of the Standard Model, such as supersymmetry and grand unified theories, aim to address these gaps. Supersymmetry proposes that each particle has a heavier superpartner, which could help unify the forces and explain dark matter. However, experimental evidence for supersymmetry remains elusive. The search for a more complete theory continues with experiments at particle accelerators, like the Large Hadron Collider. These experiments probe higher energies and smaller scales, searching for new particles and interactions that could extend our understanding beyond the Standard Model. The Standard Model also informs cosmology, helping to explain the conditions of the early universe. Particle interactions during the Big Bang shaped the evolution of the cosmos. And ongoing research in both fields aims to unify our understanding of the very large and the very small. The mathematical beauty and predictive power of the Standard Model have made it a cornerstone of modern physics. Its success is a testament to the power of scientific inquiry and collaboration, reflecting the cumulative efforts of many scientists over decades. The ongoing pursuit of knowledge in particle physics seeks to build on the foundation of the Standard Model. Each discovery brings new questions and challenges, driving the field forward and deepening our understanding of the fundamental nature of reality. Quantum electrodynamics, or QED, is the quantum field theory that describes how light and matter interact. It is one of the most precise and successful theories in physics, providing a comprehensive framework for understanding electromagnetic interactions at the quantum level. At the heart of QED is the concept of the photon, the quantum of the electromagnetic field. Photons are the force carriers of electromagnetism, mediating the interactions between charged particles like electrons and positrons. These interactions are described by the exchange of virtual photons. The mathematical formulation of QED involves the use of Feynman diagrams, which are graphical representations of the interactions between particles. Each line and vertex in a Feynman diagram corresponds to specific mathematical terms in the theory's equations, making it easier to visualize and calculate complex interactions. One of the key features of QED is the principle of gauge invariance. This principle ensures that the theory remains consistent and predictive regardless of the choice of gauge, or the mathematical framework used to describe the electromagnetic field. Gauge invariance is crucial for maintaining the theory's internal consistency. Renormalization is a vital process in QED used to handle the infinities that arise in calculations. By redefining certain parameters, physicists can absorb these infinities into measurable quantities like charge and mass, yielding finite and accurate predictions that match experimental results. QED has been tested to an extraordinary degree of precision. One of its most famous predictions is the anomalous magnetic moment of the electron, a tiny deviation from the value predicted by classical physics. Experimental measurements of this quantity agree with QED's predictions to more than 10 decimal places. The Lamb shift is another important prediction of QED. It describes a small difference in energy levels of hydrogen atoms that cannot be explained by the Dirac equation alone. The Lamb shift was experimentally observed and provided early confirmation of the accuracy of QED. QED also explains the phenomenon of vacuum polarization, where a photon temporarily creates a particle-antiparticle pair that affects the properties of the vacuum. This effect modifies the force between charged particles at very short distances and has been experimentally verified. The theory also accounts for the scattering of light by light, a process that occurs through the creation of virtual electron-positron pairs. Although extremely rare and difficult to observe, this process is a direct consequence of the principles of QED. QED has profound implications for our understanding of the nature of reality. It reveals that empty space is not truly empty, but filled with virtual particles constantly popping in and out of existence. This view challenges classical concepts of the vacuum and the nature of particles. In addition to its theoretical achievements, QED has practical applications in technology. The principles of QED underpin the operation of many modern devices, including lasers, transistors, and quantum computers, driving advancements in fields like electronics and communications. QED has also influenced other areas of physics, serving as a model for developing quantum field theories of the weak and strong nuclear forces. The techniques and concepts pioneered in QED have been adapted and expanded to create a unified framework for understanding all fundamental interactions. The development of QED was a collaborative effort involving many brilliant physicists, including Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, who shared the Nobel Prize in Physics in 1965 for their contributions. Their work laid the foundation for much of modern theoretical physics. Despite its success, QED is not the final word in our understanding of the universe. It is part of the Standard Model, which, while incredibly effective, is known to be incomplete. The search for a more comprehensive theory, one that includes gravity and explains dark matter, continues to drive research in theoretical physics. Quantum electrodynamics remains a cornerstone of our understanding of the quantum world. Its precision and predictive power exemplify the strength of the scientific method and the profound insights that arise from combining theory with experiment. As we continue to explore the quantum realm, QED will undoubtedly remain a central and influential part of our journey. Quantum chromodynamics, or QCD, is the quantum field theory that describes the strong nuclear force. This force is responsible for binding quarks together to form protons, neutrons, and other hadrons. QCD is a central part of the standard model of particle physics. The fundamental particles in QCD are quarks and gluons. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Gluons are the force carriers of the strong interaction, analogous to photons in electromagnetism, but with some crucial differences. One of the key features of QCD is color charge. Quarks carry one of 3 color charges: red, green, or blue. Gluons carry a combination of color and anticolor. The strong force acts between color charges, binding quarks together so that hadrons are color neutral. QCD is characterized by the property of confinement. Confinement means that quarks and gluons are never found in isolation. They are always confined within hadrons. This property explains why we never observe free quarks in nature, only composite particles like protons and neutrons. Asymptotic freedom is another important feature of QCD. At very high energies or short distances, the strong force becomes weaker, allowing quarks and gluons to interact more freely. This property was discovered by David Gross, Frank Wilczek, and David Politzer, who were awarded the Nobel Prize in Physics in 2004. The equations of QCD are highly complex, involving the interactions of quarks and gluons through the exchange of gluons. These interactions are described by the QCD Lagrangian, which is based on the principles of gauge invariance, similar to those in quantum electrodynamics. Calculating the properties of hadrons from first principles in QCD is a challenging task due to the strong coupling at low energies. Lattice QCD is a numerical approach that discretizes spacetime into a lattice, allowing for non-perturbative calculations of hadronic properties using powerful supercomputers. QCD explains the mass of hadrons primarily through the interactions of quarks and gluons. The masses of individual quarks are relatively small compared to the masses of protons and neutrons. The majority of hadronic mass arises from the energy of the gluon fields and the dynamic motion of quarks. Gluons themselves carry color charge, which means they can interact with each other. This self-interaction is a unique feature of QCD and leads to the complex behavior of the strong force, including phenomena like gluon confinement and the formation of glueballs, hypothetical particles made entirely of gluons. QCD also plays a crucial role in the early universe. During the first microseconds after the Big Bang, the universe was in a quark-gluon plasma state, where quarks and gluons were not confined within hadrons. Studying this state helps scientists understand the conditions and processes that shaped the early cosmos. Experiments at particle colliders, such as the Large Hadron Collider, investigate QCD by colliding protons at high energies. These collisions produce jets of particles that provide insights into the behavior of quarks and gluons and test the predictions of QCD. The strong force described by QCD is essential for nuclear physics. It explains the binding of protons and neutrons in atomic nuclei, which determines the stability and properties of elements. Understanding QCD is therefore fundamental to our knowledge of nuclear reactions, including those in stars and nuclear reactors. QCD has also led to the prediction and discovery of exotic hadrons, such as tetraquarks and pentaquarks, which are particles made of 4 and 5 quarks, respectively. These discoveries expand our understanding of how quarks can combine in ways beyond traditional mesons and baryons. Theoretical and experimental advances in QCD continue to deepen our understanding of the strong force. Research in this area not only tests the limits of the standard model, but also explores possible new physics beyond it, such as the existence of new particles or interactions. Quantum chromodynamics is a rich and intricate theory that forms the backbone of our understanding of the strong interaction. Its successful description of the strong force has revolutionized particle physics, providing profound insights into the fundamental structure of matter. The weak nuclear force is one of the 4 fundamental forces of nature. It is responsible for processes like beta decay in radioactive atoms and plays a crucial role in the fusion reactions that power the sun and other stars. Despite its name, the weak force is stronger than gravity, but weaker than both the electromagnetic and strong nuclear forces. The weak force is unique because it can change the flavor of quarks, transforming one type of quark into another. This ability to change quark flavors is essential for the process of nuclear fusion and for the synthesis of elements in stars. The weak force is mediated by three massive gauge bosons, the W+, W, and Z bosons. These particles are much heavier than protons and neutrons, which is why the weak force has such a short range. The mass of these bosons limits the range of the weak interaction to about 0.1% of the diameter of a typical atomic nucleus. One of the key features of the weak force is its violation of parity symmetry. Parity symmetry is the idea that the laws of physics should be the same if viewed in a mirror. However, experiments have shown that the weak force does not respect this symmetry, leading to surprising asymmetries in particle interactions. The discovery of parity violation in the weak force was first observed in the 1950s in experiments involving the beta decay of cobalt-60. These experiments showed that electrons were emitted preferentially in a direction opposite to the spin of the decaying nucleus, providing clear evidence of parity violation. The weak force also violates charge parity, CP symmetry, a combination of charge conjugation symmetry and parity symmetry. CP violation is a key ingredient in explaining the matter-antimatter asymmetry observed in the universe. Without CP violation, the Big Bang should have produced equal amounts of matter and antimatter, leading to their mutual annihilation. The theory that unifies the electromagnetic and weak forces is called the electro-weak theory. This theory, developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg in the 1970s, showed that at high energies, the electromagnetic and weak forces become indistinguishable. The successful unification of these forces was confirmed by the discovery of the W and Z bosons. The discovery of the W and Z bosons in the 1980s at the CERN laboratory provided strong experimental support for the electro-weak theory. These discoveries were milestones in particle physics, confirming key predictions of the Standard Model and earning their discoverers the Nobel Prize. The weak force is essential for the process of Bethe decay, where a neutron decays into a proton, an electron, and an electron antineutrino. This process is vital for the stability of atomic nuclei and for the generation of elements in stars. Neutrinos, which are nearly massless and interact very weakly with matter, are also involved in weak interactions. They are produced in large numbers in nuclear reactions, such as those in the Sun, and can pass through ordinary matter almost unhindered, making them difficult to detect. Neutrino oscillations, a phenomenon where neutrinos change flavors as they travel, are a direct consequence of the weak force and provide evidence that neutrinos have mass. The discovery of neutrino oscillations challenged the Standard Model and led to significant advancements in our understanding of particle physics. Experiments studying weak interactions, such as those involving neutrinos, continue to provide valuable insights into fundamental physics. These experiments test the limits of the Standard Model and explore possible new physics beyond it. The weak force also plays a role in the early universe, influencing the processes that led to the formation of the first elements during Big Bang nucleosynthesis. Understanding the weak force helps scientists reconstruct the conditions of the early universe and the evolution of matter. Despite its short range, the weak force is a crucial component of the Standard Model, explaining many fundamental processes in particle physics and cosmology. Its unique properties, such as flavor-changing interactions and symmetry violations, make it a fascinating area of study. The ongoing research into the weak nuclear force continues to deepen our understanding of the fundamental forces of nature. As we explore the weak interactions and their implications, we gain insights into the underlying principles that govern the universe, bringing us closer to a unified theory of everything. The concept of strings is central to string theory, a theoretical framework that attempts to reconcile quantum mechanics and general relativity. Instead of viewing fundamental particles as point-like objects, string theory proposes that they are one-dimensional strings that vibrate at different frequencies. These strings can be open, with two endpoints, or closed, forming a loop. The different vibrational modes of these strings correspond to different particles, such as quarks, electrons, and even force-carrying particles like photons and gluons. One of the most compelling features of string theory is that it naturally includes gravity. One of the vibrational modes of a closed string corresponds to a particle with properties matching those of the graviton, the hypothetical quantum particle that mediates the gravitational force. String theory requires additional dimensions of space beyond the familiar 3 dimensions. In most versions of the theory, there are a total of 10 dimensions, 9 spatial dimensions, and 1 time dimension. These extra dimensions are compactified, meaning they are curled up so small that they are not observable at everyday scales. The geometry and topology of these compactified dimensions affect the properties of the strings and, consequently, the physical characteristics of the particles. Different compactification schemes can lead to different low-energy physics, offering a rich landscape of possibilities. One of the major breakthroughs in string theory is the concept of supersymmetry, or SUSY. Supersymmetry posits that every particle has a superpartner with different spin properties. This symmetry helps resolve certain mathematical inconsistencies in the theory and has implications for particle physics beyond the standard model. In addition to supersymmetry, string theory led to the development of various string theories, such as Type 1, Type 2IA, Type 2IB, heterotic SO32, and heterotic EAXE8. These theories initially seemed distinct but were later found to be related through dualities, indicating they are different aspects of a single underlying theory. The unification of these string theories under one framework led to the development of M-theory, which suggests an 11-dimensional universe. In M-theory, strings can also manifest as 2-dimensional membranes, or branes, further enriching the structure of the theory. String theory also introduces the concept of D-branes, which are objects where open strings can end. These branes can have various dimensions and play a crucial role in understanding non-perturbative aspects of the theory. They provide a way to incorporate gauge theories and other structures within the string framework. The holographic principle is another significant insight derived from string theory. It suggests that all the information contained within a volume of space can be represented as a theory on the boundary of that space. This principle has profound implications for understanding quantum gravity and black hole thermodynamics. Despite its elegance and potential, string theory is still largely theoretical, with many aspects yet to be confirmed experimentally. The energy scales at which string theory's predictions become relevant are far beyond the reach of current particle accelerators, making direct verification challenging. However, string theory has provided deep insights into mathematics and theoretical physics. Concepts from string theory have led to advances in understanding topology, geometry, and the structure of space-time. These contributions highlight the theory's potential, even if its full physical implications are not yet clear. String theory also offers a potential framework for unifying all fundamental forces, including gravity, into a single coherent theory. This goal, often referred to as the search for a theory of everything, drives much of the research in this field. The development of string theory has been marked by both breakthroughs and challenges. While it has not yet achieved all its goals, it remains one of the most ambitious and comprehensive attempts to understand the fundamental nature of reality. As research continues, string theory may provide the answers to some of the most profound questions in physics. Whether it ultimately succeeds or leads to new theories, its impact on our understanding of the universe is undeniable. In string theory, dimensions play a crucial role in defining the structure and behavior of the universe. Unlike the familiar 3 dimensions of space and 1 of time, string theory proposes additional spatial dimensions. The theory suggests that the universe has 10 dimensions, 9 spatial dimensions and 1 time dimension. These extra dimensions are compactified, meaning they are curled up into tiny, complex shapes that are too small to be observed directly. The specific shape and size of these compactified dimensions affect the physical properties of strings and, consequently, the behavior of particles and forces in our observable universe. The different possible configurations of these dimensions lead to a variety of potential physical laws. One popular model for compactifying these extra dimensions is called a Calabi-Yau manifold. These are complex, multidimensional shapes that allow for the consistency of string theory. The geometry of Calabi-Yau manifolds plays a significant role in determining the properties of particles and forces. The concept of branes, or membranes, extends the idea of dimensions in string theory. Branes can have various dimensionalities and can exist within the higher dimensional space proposed by the theory. For example, a D3 brane has 3 spatial dimensions, while a D5 brane has 5. Interactions between branes and strings lead to a rich tapestry of physical phenomena. Open strings can have their endpoints attached to branes, and these interactions can describe fundamental particles and gauge forces, offering a potential explanation for the diversity of particles observed in nature. M-theory, an extension of string theory, posits an 11-dimensional universe, adding an extra spatial dimension. In M-theory, strings are seen as one-dimensional slices of two-dimensional membranes, or branes, that can exist in higher dimensional spaces. The additional dimensions in string theory can help resolve several issues in theoretical physics. For instance, they provide a natural framework for unifying the forces of nature, including gravity, into a single coherent theory. These dimensions also help to cancel out certain anomalies that would otherwise render the theory inconsistent. Exploring the implications of these extra dimensions requires sophisticated mathematical tools. The study of higher dimensional spaces has led to significant advancements in fields like algebraic geometry and topology, showing the deep interconnection between mathematics and theoretical physics. The presence of extra dimensions could potentially be detected through experiments, such as those conducted at particle colliders like the Large Hadron Collider. For instance, the production of microscopic black holes or deviations from the inverse square law of gravity at small scales could provide evidence for these dimensions. The idea of extra dimensions also has implications for cosmology. It can influence the early universe's behavior, including inflation, the period of rapid expansion shortly after the Big Bang. These dimensions may also play a role in the formation and behavior of cosmic structures. String theory's extra dimensions can also impact the fundamental constants of nature, such as the strengths of the forces and the masses of particles. The specific configuration of these dimensions can lead to different vacua, or possible states of the universe, each with its own physical properties. The landscape of string theory includes a vast number of possible configurations for these extra dimensions, leading to the idea of the multiverse. This suggests that our universe might be just one of many, each with different physical laws and constants shaped by their own compactified dimensions. While the idea of extra dimensions may seem abstract, it provides a powerful framework for addressing some of the most profound questions in physics. By exploring these dimensions, string theorists hope to uncover the fundamental principles governing the universe. Research into the dimensions of string theory continues to be a vibrant and evolving field. As theoretical and experimental tools advance, we may come closer to understanding the true nature of these hidden dimensions and their role in the fabric of reality. String theory is not a single theory but a collection of related theories, each with its own unique features and characteristics. These different types of string theories were initially developed independently, but were later found to be connected through various dualities. Type Y string theory includes both open and closed strings. It is unique in allowing for the existence of unoriented strings, which means that the strings do not have a definite direction. This theory includes both D-branes and orientifold planes, providing a rich structure for particle interactions. Type YA string theory consists solely of closed strings. It is non-chiral, meaning that it does not distinguish between left-handed and right-handed particles. The low energy limit of type YA string theory corresponds to a 10-dimensional supergravity theory. Type IIB string theory also consists solely of closed strings, but differs from type 2IA in being chiral. This means that it distinguishes between left-handed and right-handed particles. Type IIB string theory includes self-dual forms, adding complexity to its structure and interactions. Heterotic string theories come in two main types, heterotic SO32 and heterotic E8XE8. These theories combine the features of both bosonic strings and superstrings, with right-moving modes described by a superstring and left-moving modes described by a bosonic string. The heterotic E8XE8 theory is particularly interesting for its potential in unifying all fundamental forces, including gravity, in a consistent manner. Type 1 and Type 2 string theories are also distinguished by the presence or absence of supersymmetry. Type 1 string theory is supersymmetric in 10 dimensions, while Type 2 string theories exhibit extended supersymmetry, providing a higher degree of symmetry and constraints. These string theories are connected by various dualities. T-duality relates Type 2EA and Type IIB string theories, suggesting that a compactified dimension in one theory corresponds to a different compactification in the other. This duality reveals deep connections between seemingly distinct theories. S-duality connects Type 1 string theory to the heterotic SO32 string theory, showing that strong coupling in one theory corresponds to weak coupling in the other. This relationship highlights the non-perturbative aspects of string theory, where the behavior of strings at strong coupling can be understood through dual theories. Another important duality is U-duality, which encompasses both T-duality and S-duality. U-duality provides a unified framework that relates all 5 consistent superstring theories, suggesting that they are different limits of a single underlying theory. These dualities led to the development of M-theory, which posits an 11-dimensional framework that includes all 5 string theories as different aspects. M-theory suggests that at higher energies, the distinctions between the different string theories blur, revealing a more fundamental theory. M-theory introduces new objects called membranes, or M-branes, which extend the concept of strings to higher dimensions. These branes play a crucial role in the non-perturbative dynamics of the theory, adding to the richness and complexity of string interactions. The landscape of string theories offers a multitude of possible vacua, each corresponding to a different configuration of the compactified dimensions. This landscape, sometimes referred to as the string theory landscape, provides a vast array of possible physical laws and constants. The exploration of these different string theories and their connections through dualities has deepened our understanding of fundamental physics. It has revealed unexpected relationships between seemingly unrelated theories and opened new avenues for research. The study of string theories continues to be an active and evolving field, with ongoing efforts to understand their implications for both high-energy physics and cosmology. Each type of string theory contributes to a more comprehensive picture of the fundamental structure of the universe. As research progresses, the hope is that these insights will lead to a unified theory of everything, bridging the gap between quantum mechanics and general relativity, and providing a deeper understanding of the underlying principles of nature. Supersymmetry, often abbreviated as SUSY, is a theoretical framework that extends the standard model of particle physics. It proposes a symmetry between fermions, which make up matter, and bosons, which carry forces. This symmetry could solve many outstanding problems in physics. One of the key roles of supersymmetry is addressing the hierarchy problem. This problem involves the vast difference in strength between gravity and the other fundamental forces. SUSY helps to stabilize the Higgs boson's mass against large quantum corrections, making it naturally small and resolving the hierarchy issue. Supersymmetry predicts the existence of superpartners for each known particle. For every fermion, there is a corresponding boson and vice versa. These superpartners have the same properties except for their spin, which differs by half a unit. For example, the electron would have a superpartner called the selectron. The inclusion of superpartners doubles the number of particles in the theory, leading to a richer and more complex particle spectrum. These superpartners have not yet been observed experimentally, but their discovery would provide strong evidence for supersymmetry. Another significant role of supersymmetry is in unifying the fundamental forces. At high energy scales, the strengths of the electromagnetic, weak and strong forces converge. SUSY improves the precision of this unification, suggesting that all forces could indeed be unified at a high energy scale. Supersymmetry also provides a candidate for dark matter, an unknown substance that makes up about 27% of the universe. The lightest supersymmetric particle, often called the neutralino, is stable and interacts weakly with ordinary matter, making it a prime candidate for dark matter. In string theory, supersymmetry is essential for consistency. It allows for the cancellation of anomalies that would otherwise render the theory inconsistent. SUSY also helps to stabilize the vacuum, preventing rapid changes that would be incompatible with our observed universe. Supersymmetry has significant implications for cosmology, It affects the behavior of the early universe, including inflation, a rapid expansion that occurred shortly after the Big Bang. SUSY particles could play a role in driving inflation and shaping the universe's large-scale structure. The search for supersymmetry is a major focus of experimental physics, particularly at particle colliders like the Large Hadron Collider. These experiments aim to produce and detect superpartners, providing direct evidence for SUSY and shedding light on the fundamental nature of matter. If discovered, supersymmetry would revolutionize our understanding of the universe. It would extend the Standard Model, providing a more complete and unified framework for describing all known particles and forces. SUSY could also open new avenues for research in both theoretical and experimental physics. The mathematical structure of supersymmetry is elegant and powerful, offering deep insights into the nature of space and time. SUSY transformations relate different types of particles in a way that preserves the symmetries of space-time, leading to a more unified description of the physical world. Supersymmetry also has implications for quantum gravity. It is a key component of superstring theory, which aims to unify gravity with the other fundamental forces. SUSY provides the necessary framework for the extra dimensions and complex interactions predicted by string theory. Despite its theoretical appeal, supersymmetry faces challenges. The lack of experimental evidence for superpartners at the energy scales probed so far raises questions about its validity. However, higher energy experiments and more sensitive detectors may yet reveal SUSY particles. The ongoing pursuit of supersymmetry exemplifies the interplay between theory and experiment in physics. SUSY remains one of the most promising avenues for discovering new physics beyond the Standard Model, with the potential to answer fundamental questions about the universe. As research continues, the role of supersymmetry in shaping our understanding of the cosmos remains a central focus. Whether it is ultimately confirmed or refuted, the quest for SUSY will undoubtedly deepen our knowledge and drive the future of particle physics. String theory, despite its elegance and potential, faces numerous challenges and criticisms. One of the primary criticisms is its lack of empirical evidence. No experimental data have yet confirmed the existence of strings or extra dimensions. Another significant challenge is the energy scale at which string theory becomes relevant. The Planck scale, where string effects are expected to become significant, is far beyond the reach of current or foreseeable particle accelerators. This makes direct experimental tests of string theory extremely difficult. The vast number of possible solutions in string theory, often referred to as the landscape, is another criticism. The theory allows for an enormous number of possible vacua, each corresponding to different physical laws. Critics argue that this makes the theory less predictive and more difficult to falsify. String theory also struggles with the problem of uniqueness. With so many possible solutions, it's unclear why our universe has the specific properties it does. This lack of uniqueness raises questions about the explanatory power of the theory. Mathematical complexity is another challenge. The equations of string theory are highly complex and require advanced mathematical tools to solve. This complexity can be a barrier to progress and makes the theory less accessible to physicists who are not specialists in the field. The problem of background dependence is a significant theoretical issue. Most formulations of string theory assume a fixed space-time background, but a complete theory of quantum gravity should be background independent. This limitation suggests that string theory may not yet be fully formulated. String theory's reliance on supersymmetry, while providing many theoretical advantages, also brings challenges. Supersymmetry has not been observed experimentally, and the lack of evidence from the Large Hadron Collider and other experiments casts doubt on this aspect of the theory. Critics also point out the theory's failure to provide a clear and testable prediction that distinguishes it from other theories. While string theory offers explanations for many fundamental aspects of physics, it has yet to deliver a unique, falsifiable prediction that can be tested experimentally. Another criticism is the theory's perceived disconnect from observable phenomena. While string theory addresses fundamental questions about the nature of the universe, it often seems far removed from practical, testable physics. This disconnect can make the theory seem speculative to some physicists. The issue of the anthropic principle is also contentious. Some interpretations of string theory suggest that the properties of our universe may be explained by the anthropic principle, which states that the universe must allow for the existence of observers like us. This idea is controversial and considered unscientific by many. The lack of a fully understood mechanism for compactifying extra dimensions is another challenge. While various methods such as Calabi-Yau manifolds have been proposed, a definitive solution remains elusive. Understanding how these dimensions are compactified is crucial for making contact with observable physics. The potential for string theory to unify all fundamental forces is a significant motivation, but the path to unification remains unclear. Despite decades of research, a complete and consistent theory that unifies gravity with the other forces has not yet been achieved. Theoretical physicists also debate the role of string theory in the broader landscape of physics. Some argue that the focus on string theory may be limiting exploration of other promising avenues, potentially overlooking alternative approaches to understanding fundamental physics. Despite these challenges, string theory has driven significant advances in mathematics and theoretical physics. It has provided new insights into black holes, quantum field theory, and the nature of space-time. These contributions underscore the theory's importance, even as it faces criticism. The ongoing dialogue between proponents and critics of string theory is essential for the progress of science. By addressing these challenges and criticisms, researchers can refine and test the theory, contributing to our understanding of the fundamental nature of the universe. Loop quantum gravity, often abbreviated as LQG, is an approach to unifying quantum mechanics and general relativity. It aims to describe the quantum properties of space-time itself. Unlike string theory, which posits extra dimensions and fundamental strings, LQG focuses on the fabric of space-time. At the core of loop quantum gravity is the idea that space-time is not continuous. Instead, it is made up of discrete, finite loops woven into a fine fabric or network. These loops are incredibly small, on the order of the Planck length, which is about 10 to 35 meters. LQG proposes that the geometry of space-time is quantized. This means that quantities like area and volume have discrete values. These quantized units are derived from the spin network, a mathematical structure used to represent quantum states of the gravitational field. Spin networks are graphs composed of edges and nodes. The edges are labeled by spins, which represent the quantum states of the gravitational field. These networks evolve over time, and their evolution is described by spin foams, which are higher dimensional analogues of spin networks. In loop quantum gravity, space is not a smooth continuum but has a granular structure. The quantization of space-time suggests that space is composed of tiny, discrete chunks, similar to how energy is quantized in quantum mechanics. The theory does not require a background space-time to exist. Instead, space-time geometry emerges from the quantum properties of the spin networks. This background independence is a significant feature of LQG, distinguishing it from many other approaches to quantum gravity. One of the major achievements of LQG is the derivation of the spectra of geometric operators. These operators measure areas and volumes, and their spectra are discrete. This result implies that space itself has an atomic structure at the smallest scales. Loop quantum gravity also offers insights into the nature of black holes. The theory provides a framework for understanding black hole entropy, suggesting that the entropy is proportional to the area of the event horizon. This result is consistent with the Bekenstein-Hawking formula, derived from classical general relativity and quantum field theory. LQG has led to the development of loop quantum cosmology, which applies the principles of LQG to the entire universe. This approach provides new insights into the early universe, particularly the conditions near the Big Bang. It suggests that the Big Bang may be replaced by a Big Bounce, where a previous contracting phase is followed by expansion. One of the key challenges for LQG is finding a complete and consistent set of equations that describe the dynamics of spin networks. While significant progress has been made, the theory is still under development, and many details remain to be worked out. LQG does not require supersymmetry or extra dimensions, making it a more conservative approach compared to string theory. This simplicity appeals to many physicists who prefer a more straightforward extension of known physical principles. Experimental tests of LQG are challenging due to the extremely small scales involved. However, Researchers are exploring potential observational signatures, such as deviations from the classical behavior of black holes and cosmological phenomena. The interplay between LQG and other theories of quantum gravity, such as string theory, is an area of active research. Some physicists are investigating whether these approaches can be reconciled or if they represent fundamentally different paths to understanding quantum gravity. Loop quantum gravity has also inspired new mathematical techniques and insights, contributing to the broader field of theoretical physics. Its emphasis on background independence and the discrete nature of space-time has influenced various areas of research. As the development of loop quantum gravity continues, it holds promise for providing a deeper understanding of the quantum nature of space-time. Its ongoing exploration is crucial for the quest to unify the fundamental forces and to comprehend the true nature of the universe. Spin networks are a fundamental concept in loop quantum gravity, representing the quantum states of the gravitational field. They provide a way to visualize and calculate the geometry of space-time at the quantum level. A spin network is a graph composed of nodes and edges. The edges are labeled with spins, which correspond to the quantized units of area, and the nodes represent the intersections where these quantum areas meet. These networks are not fixed but can change and evolve. The spins on the edges can change, and the connections between nodes can be reconfigured, reflecting the dynamic nature of space-time in loop quantum gravity. Spin networks were introduced by Roger Penrose in the 1970s as a way to describe the quantum geometry of space. In loop quantum gravity, they have been adapted to provide a rigorous mathematical framework for understanding quantum space-time. The edges of spin networks are associated with representations of the SU2 group, which is related to the intrinsic spin of particles. The labels on the edges represent the quantum states of the gravitational field, with each state corresponding to a specific geometry. Nodes in spin networks represent regions where these quantum areas come together. The number of edges meeting at a node and their spins determine the volume associated with that node. Thus, spin networks provide a way to calculate both areas and volumes in quantum spacetime. The evolution of spin networks over time is described by spin foams. Spin foams are higher dimensional generalizations of spin networks, representing the history of a spin network as it changes from one configuration to another. They provide a way to understand the dynamics of spacetime in loop quantum gravity. The use of spin networks and spin foams allows loop quantum gravity to describe the geometry of spacetime without reference to a fixed background. This background independence is a significant advantage of the theory, aligning with the principles of general relativity. One of the key insights from spin networks is that areas and volumes are quantized. This means that space itself is composed of discrete units, much like energy levels in quantum mechanics. This quantization leads to a granular structure of spacetime at the smallest scales. Spin networks also help to explain the entropy of black holes. By counting the number of possible spin network configurations that correspond to a given black hole horizon, researchers can derive the black hole's entropy, providing a quantum mechanical explanation for this classical property. The mathematical tools used to analyze spin networks include techniques from combinatorics and representation theory. These tools help physicists calculate the properties of quantum spacetime and make predictions that can be tested against observations. Spin networks provide a framework for understanding the quantum states of spacetime, but they also pose challenges. Calculating the evolution of spin networks is complex, and finding exact solutions requires sophisticated mathematical techniques. Despite these challenges, spin networks offer a promising approach to understanding the fundamental nature of spacetime. They provide a clear and intuitive picture of how space might be structured at the quantum level. Research into spin networks continues to evolve, with new methods and insights being developed. As our understanding of these networks improves, they may provide crucial clues for unifying quantum mechanics and general relativity. Spin networks are a key component of loop quantum gravity, offering a novel way to think about space and time. By quantizing the geometry of spacetime, they open new avenues for exploring the quantum nature of the universe and the fundamental forces that govern it. Quantum geometry is a fundamental concept in loop quantum gravity, describing the structure of space at the smallest scales. Unlike classical geometry, which is continuous, quantum geometry is discrete and quantized. In quantum geometry, the properties of space, such as area and volume, come in discrete units. These units are determined by the quantum states of the gravitational field, represented by spin networks. This quantization of geometry means that space is not a smooth continuum, but is made up of tiny, discrete chunks. This granular structure is a significant departure from the continuous space of classical physics. The quantization of geometry is described mathematically by operators that measure areas and volumes. These operators have discrete spectra, meaning their possible values are quantized. This is similar to how energy levels in an atom are quantized in quantum mechanics. One of the key insights from quantum geometry is that the fabric of space-time itself is composed of these discrete units. This idea provides a new way of thinking about the nature of space and time, with implications for our understanding of the universe. Quantum geometry also plays a crucial role in the description of black holes. By counting the quantum states associated with a black hole's event horizon, physicists can calculate its entropy, providing a quantum mechanical explanation for this classical property. The discrete nature of quantum geometry also has implications for the Big Bang. It suggests that the singularity at the beginning of the universe may be replaced by a finite, quantized structure, potentially resolving some of the infinities that arise in classical theories. Quantum geometry is described using the language of spin networks in loop quantum gravity. These networks represent the quantum states of space, with the connections and labels on the network corresponding to the geometry's discrete properties. Spin foams extend this concept to include the evolution of quantum geometry over time. They provide a way to understand how the geometry of space changes at the quantum level, offering insights into the dynamics of space-time. The study of quantum geometry requires sophisticated mathematical tools, including techniques from combinatorics and representation theory. These tools help physicists calculate the properties of quantum space-time and make predictions that can be tested against observations. One of the challenges in quantum geometry is understanding how the smooth, continuous space-time of general relativity emerges from the discrete structure described by spin networks. This process, known as the classical limit, is a major area of research in loop quantum gravity. Quantum geometry also has implications for the understanding of the early universe. It suggests that the initial conditions of the universe were governed by quantum effects, potentially leading to new insights into the nature of the Big Bang and cosmic inflation. The concept of quantum geometry extends beyond loop quantum gravity and has applications in other areas of physics, including string theory and quantum cosmology. It provides a unifying framework for understanding the quantum aspects of space-time. Research into quantum geometry is ongoing, with physicists continually developing new methods and insights. As our understanding of quantum geometry improves, it may lead to breakthroughs in our understanding of the fundamental nature of the universe. Quantum geometry offers a profound new way of thinking about space and time. By describing the structure of space-time at the smallest scales, it provides a bridge between quantum mechanics and general relativity, bringing us closer to a unified theory of quantum gravity. Loop quantum gravity and string theory are two prominent approaches to quantum gravity, but they differ significantly in their fundamental concepts and methods. One of the main differences is their starting point. Loop quantum gravity focuses on quantizing spacetime itself, while string theory posits that the fundamental building blocks are one-dimensional strings. String theory requires additional spatial dimensions beyond the familiar 3. Typically, string theory operates in 10 or 11 dimensions, depending on the specific formulation. In contrast, loop quantum gravity works with the 4-dimensional spacetime of general relativity, without requiring extra dimensions. The mathematical structures used in these theories are also different. Loop quantum gravity uses spin networks and spin foams to represent quantum states and their evolution, respectively. String theory, on the other hand, employs the mathematical framework of string perturbation theory and conformal field theory. Another key difference is their approach to unification. String theory aims to unify all fundamental forces, including gravity, by treating particles as different vibrational modes of strings. Loop quantum gravity focuses solely on quantizing the gravitational field, leaving the unification of other forces as a separate issue. String theory incorporates supersymmetry, which posits a symmetry between fermions and bosons. This extension helps address several theoretical issues, but has yet to be confirmed experimentally. Loop quantum gravity does not rely on supersymmetry, making it a more conservative extension of general relativity. Loop quantum gravity is background independent, meaning it does not presuppose a fixed spacetime background. The geometry of spacetime emerges from the quantum properties of the spin networks. String theory typically assumes a fixed background spacetime, although there are efforts to formulate a background-independent version. The physical predictions of these theories also differ. String theory predicts the existence of various higher-dimensional objects, such as branes, and a plethora of new particles, including those predicted by supersymmetry. Loop quantum gravity predicts a discrete structure of spacetime and potential deviations from classical general relativity at very small scales. Experimental verification is a significant challenge for both theories. String theory's predictions, such as supersymmetric particles, require energies far beyond current experimental capabilities. Loop quantum gravity's predictions, such as the quantization of spacetime, also require highly sensitive experiments, but may be testable through observations of black holes or cosmic phenomena. The two theories have different implications for black hole physics. String theory provides a framework for understanding the microscopic structure of black holes, using concepts like the holographic principle and D-branes. Loop quantum gravity offers a quantum description of black hole horizons and entropy through spin networks. In cosmology, string theory provides models for inflation and the early universe, including mechanisms for resolving singularities. Loop quantum gravity offers alternative scenarios, such as the Big Bounce, replacing the classical Big Bang singularity with a quantum transition. String theory's landscape of solutions, known as the string theory landscape, suggests a vast number of possible universes with different physical laws. Loop quantum gravity does not have a similar landscape, focusing instead on the quantization of a single spacetime framework. Both theories have led to significant mathematical and theoretical developments beyond their original scopy. String theory has influenced fields such as condensed matter physics and quantum computing, while loop quantum gravity has provided new insights into the nature of space and time. Despite their differences, there are ongoing efforts to find connections between loop quantum gravity and string theory. Some researchers explore whether these approaches could be complementary, providing different perspectives on a deeper underlying theory of quantum gravity. The choice between loop quantum gravity and string theory often depends on philosophical preferences and research goals. Some physicists are drawn to the unifying ambitions of string theory, while others prefer the more direct approach to quantizing spacetime offered by loop quantum gravity. Ultimately, both loop quantum gravity and string theory represent ambitious and innovative attempts to understand the quantum nature of gravity. Continued research in both areas will deepen our understanding of the universe and may eventually lead to a coherent theory that unifies these approaches. Current research in quantum gravity, both in string theory and loop quantum gravity, is vibrant and multifaceted. Physicists are exploring new ideas, refining existing theories, and seeking ways to test these theories experimentally. In string theory, researchers are delving deeper into the landscape of solutions. They aim to understand how different compactifications of extra dimensions can lead to different physical laws and what this means for the potential existence of multiple universes. The ADS-CFT correspondence, a powerful tool in string theory, continues to provide insights. This duality relates a gravitational theory in a higher dimensional space to a conformal field theory on its boundary. It has applications in understanding black holes, quantum field theory, and even condensed matter systems. Efforts to formulate a background-independent version of string theory are ongoing. Such a formulation would not require a pre-existing spacetime, aligning string theory more closely with the principles of general relativity and loop quantum gravity. Supersymmetry remains a key focus in string theory. Researchers are studying its implications for particle physics and cosmology, even as experimental searches at the Large Hadron Collider continue to probe for evidence of superpartners. In loop quantum gravity, significant progress has been made in understanding the dynamics of spin networks and spin foams. These structures describe the quantum states of spacetime and their evolution, providing a picture of quantum geometry. Loop quantum cosmology, an application of loop quantum gravity to the entire universe, offers new models for the early universe. Researchers are exploring the idea of the Big Bounce and how quantum effects could have influenced the evolution of the cosmos. The study of black holes within loop quantum gravity is another active area. Physicists are investigating how quantum geometry affects black hole entropy and the nature of singularities, potentially leading to new insights into the information paradox. Experimental efforts to test predictions of loop quantum gravity are underway. Researchers are looking for potential signatures in the cosmic microwave background, gravitational waves, and high-energy astrophysical phenomena that could provide evidence for the theory's discrete spacetime structure. Both string theory and loop quantum gravity are influencing other fields. Techniques from string theory are being applied to problems in condensed matter physics, leading to new understandings of materials and quantum phase transitions. Loop quantum gravity's emphasis on background independence and discrete spacetime has inspired new approaches in quantum computing and quantum information theory. These ideas could lead to advances in how we process and understand information at the quantum level. Interdisciplinary collaborations are becoming increasingly common. Physicists, mathematicians, and computer scientists are working together to tackle complex problems using tools and concepts from both string theory and loop quantum gravity. Theoretical developments are complemented by advances in experimental technology. Improvements in particle detectors, gravitational wave observatories, and cosmological surveys are providing new data that could test the predictions of quantum gravity theories. The search for a theory of everything remains a driving force. Researchers in both string theory and loop quantum gravity are motivated by the goal of unifying all fundamental forces into a single, coherent framework that explains the workings of the universe at all scales. Educational initiatives and public outreach are also playing a role in advancing the field. As more people become aware of the exciting developments in quantum gravity, there is an increasing interest in studying these theories and contributing to their progress. Current research in quantum gravity is marked by a sense of excitement and possibility. As we continue to explore the frontiers of physics, the insights gained from both string theory and loop quantum gravity will undoubtedly deepen our understanding of the universe and bring us closer to solving the mysteries of the quantum realm. The unification of string theories is a significant achievement in theoretical physics, suggesting that all 5 consistent superstring theories are different aspects of a single underlying theory. This unification is known as M-theory. M-theory posits that what we perceive as different string theories are actually different limits of a more fundamental 11-dimensional theory. This theory encompasses Type 1, Type 2IA, Type IIB, heterotic SO32, and heterotic E8xe8 string theories. The discovery of dualities between string theories was a key step towards unification. T-duality relates Type 2A and Type IIB string theories by showing that a string compactified on a small circle in one theory corresponds to a string on a large circle in the other. S-duality reveals a connection between Type 1 string theory and heterotic SO32 string theory, demonstrating that strong coupling in one theory corresponds to weak coupling in the other. This duality highlights the non-perturbative aspects of string theory. U-duality combines both T-duality and S-duality, providing a comprehensive framework that links all 5 string theories. This intricate web of dualities suggests that they are not separate theories, but different perspectives on a single, unified theory. M-theory introduces the concept of membranes, or M-branes, which are higher dimensional objects. These include 2-dimensional membranes and 5-dimensional branes, extending the idea of one-dimensional strings to more complex entities. In M-theory, strings can be viewed as one-dimensional slices of 2-dimensional membranes. This perspective unifies the different types of strings and branes, showing how they emerge from the same fundamental theory. The 11th dimension in M-theory is crucial for its consistency. When this extra dimension is compactified, it can lead to the various 10-dimensional string theories, depending on how the compactification is performed. M-theory also provides a framework for understanding the holographic principle, which suggests that all the information contained in a volume of space can be described by a theory on its boundary. This principle has profound implications for understanding black holes and quantum gravity. Unification through M-theory has led to significant insights into black hole physics. By interpreting black holes as configurations of branes, M-theory offers a microscopic explanation for their entropy, matching the Bekenstein-Hawking formula. The connections revealed by M-theory have advanced our understanding of the landscape of string vacua. This landscape includes a vast number of possible solutions, each corresponding to a different configuration of the extra dimensions and leading to different physical laws. Despite these advances, M-theory is still not fully understood. The complete formulation of M-theory remains an open question, and much work is needed to uncover its full implications and predictions. M-theory has inspired new mathematical developments, particularly in areas such as topology and geometry. These mathematical tools are essential for exploring the complex structures predicted by the theory. The unification of string theories through M-theory has brought physicists closer to the goal of a theory of everything. It suggests that the fundamental forces and particles of nature can be understood as different manifestations of a single underlying framework. As research continues, M-theory remains a promising avenue for uncovering the deepest principles of the universe. The unification of string theories is a testament to the power of theoretical physics to reveal the hidden connections that underlie the fabric of reality. The concept of membranes, or branes, is fundamental in string theory and M-theory. Branes are multidimensional objects that generalize the concept of strings to higher dimensions. A brane can have various dimensions, with a one-dimensional brane being a string, a two-dimensional brane being a membrane, and higher dimensional branes extending this idea further. These branes can exist in different spatial dimensions within the higher dimensional framework of string theory and M-theory. Branes play a crucial role in the dynamics of string theory. Open strings can have their endpoints attached to branes, leading to a rich structure of interactions and constraints that shape the physical properties of the strings. The study of D-branes, a particular type of brane, has been especially fruitful. D-branes are defined by the Dirichlet boundary conditions they impose on open strings. They have become a central tool in understanding non-perturbative aspects of string theory. D-branes can carry charges associated with various fields, and their interactions can describe gauge theories. This connection has led to deep insights into the nature of forces and particles, linking string theory to observable physical phenomena. Branes also provide a framework for understanding black holes within string theory. Certain configurations of branes can correspond to black hole solutions, offering a microscopic description of their properties, such as entropy. In M-theory, the concept of branes is extended further. M-theory includes objects like M2 branes and M5 branes, which are two-dimensional and five-dimensional, respectively. These higher dimensional branes are essential for the theory's consistency and richness. The dynamics of branes are governed by their world volume, the space in which they exist and move. The world volume dynamics can be described by various field theories, depending on the brane's dimensions and the background spacetime. Branes can intersect and interact in complex ways, leading to the creation of new branes or the transfer of charge and energy between them. These interactions are crucial for understanding the full spectrum of possibilities within string theory and M-theory. The notion of branes has also led to the development of the ADS-CFT correspondence, a powerful duality that relates a gravitational theory in a higher dimensional anti-de Sitter space to a conformal field theory on its boundary. This duality has profound implications for both theoretical physics and mathematics. Branes are also central to the study of the holographic principle, which suggests that the information content of a volume of space can be encoded on its boundary. This principle has been instrumental in advancing our understanding of black hole thermodynamics and quantum gravity. The concept of branes has provided new tools for exploring the landscape of string vacua. Different brane configurations can lead to different physical laws, helping to explain the diversity of possible universes predicted by string theory. Branes have also influenced other areas of physics, such as condensed matter systems. Concepts from brane dynamics have been applied to understand phenomena like quantum Hall effects and superconductivity, demonstrating the broad impact of these ideas. Research into branes continues to be a vibrant area of theoretical physics. Ongoing studies aim to uncover new properties of branes, explore their interactions, and understand their role in the broader framework of quantum gravity. The concept of membranes, or branes, has fundamentally changed our understanding of the universe's structure. By extending the idea of strings to higher dimensions, branes provide a richer and more flexible framework for exploring the fundamental nature of reality. As research progresses, branes will undoubtedly remain a central focus in the quest to unify the fundamental forces and understand the deep structure of the cosmos. Higher dimensions are a fundamental aspect of string theory and M-theory. Unlike our familiar three-dimensional space, these theories require additional spatial dimensions to be consistent. In string theory, there are typically 10 dimensions, 9 spatial dimensions, and 1 time dimension. M-theory extends this to 11 dimensions, adding even more complexity and potential for understanding the universe. These extra dimensions are not directly observable because they are compactified. This means they are curled up into tiny shapes, often at the Planck scale, which is about 10 to 35 meters. This compactification makes them effectively invisible at everyday scales. The shape and size of these compactified dimensions have significant implications for the physical properties of particles and forces. Different compactifications can lead to different physical laws, explaining the variety of phenomena observed in our universe. Calabi-Yau manifolds are a popular way to compactify the extra dimensions in string theory. These complex, multidimensional shapes preserve the supersymmetry required by string theory and allow for a consistent description of particles and forces. The study of higher dimensions has led to the concept of branes, which are higher dimensional objects within these theories. Branes can exist in various dimensions and play crucial roles in the dynamics of strings and the interactions between particles. In higher dimensional theories, gravity can propagate through all dimensions, while other forces might be confined to lower dimensional branes. This idea helps to explain why gravity appears so much weaker than the other fundamental forces. The presence of higher dimensions also has profound implications for cosmology. The early universe might have experienced different physical laws due to the configuration of these dimensions, influencing the formation and evolution of cosmic structures. Experiments at particle colliders like the Large Hadron Collider are searching for evidence of higher dimensions. Signs of extra dimensions could include the production of mini black holes or deviations from the expected behavior of particles at high energies. Theories with higher dimensions also suggest the possibility of parallel universes. These universes could have different physical laws, depending on the configuration of their compactified dimensions. This idea expands our understanding of the cosmos and our place within it. Mathematically, higher dimensions require sophisticated tools from geometry and topology. The study of these dimensions has led to significant advances in these fields, influencing both physics and mathematics. Higher dimensions also play a role in the holographic principle, which posits that all the information within a volume of space can be represented on its boundary. This principle has deep implications for our understanding of black holes and quantum gravity. String theory's higher dimensions offer a framework for unifying all fundamental forces, including gravity, into a single, coherent theory. This unification remains one of the primary goals of theoretical physics, driving much of the research in this area. While direct evidence for higher dimensions remains elusive, their implications continue to inspire new experiments and theoretical developments. The quest to understand these dimensions is at the forefront of the search for a deeper understanding of the universe. As research progresses, the study of higher dimensions will undoubtedly provide new insights into the fundamental nature of reality. These dimensions, though hidden from everyday experience, hold the key to unlocking some of the deepest mysteries of the cosmos. Dualities in M-theory are profound connections that link different string theories, suggesting they are all aspects of a single underlying theory. These dualities reveal deep relationships between seemingly distinct physical theories and are a cornerstone of modern theoretical physics. One of the most well-known dualities is T-duality. T-duality shows that a string compactified on a small circle in one string theory can be equivalent to a string compactified on a large circle in another string theory. This duality connects type 2a and type 2ib string theories and demonstrates that the size of the compactified dimension can be inverted without changing the physical theory. S-duality is another crucial duality, relating the strong coupling regime of one theory to the weak coupling regime of another. For example, S-duality connects type 1 string theory with the heterotic SO32 string theory, providing insights into non-perturbative aspects of these theories. U-duality combines aspects of both T-duality and S-duality, creating a more comprehensive framework that links all 5 consistent superstring theories. U-duality suggests that these theories are not separate, but rather different limits of a single, more fundamental theory known as M-theory. The ADS-CFT correspondence, also known as gauge-gravity duality, is a specific example of a duality in M-theory. It relates a gravitational theory in a higher dimensional anti-de Sitter, AD-say space, to a conformal field theory, CFT, on its boundary. This duality provides a powerful tool for studying quantum gravity and has applications in various areas of physics. Mirror symmetry is another important duality in M-theory. It connects different Calabi-Yau manifolds, showing that two seemingly different geometric spaces can lead to equivalent physical theories. Mirror symmetry has significant implications for both string theory and mathematics, particularly in the study of complex geometry. These dualities suggest that space and time can be reinterpreted in different ways, depending on the physical context. They highlight the flexibility and richness of M-theory, offering multiple perspectives on the same underlying reality. The existence of dualities challenges our traditional understanding of physical theories. Instead of viewing them as distinct and separate, dualities show that they can be different facets of a single, interconnected framework. This realization has profound implications for how we understand the nature of the universe. Dualities also play a crucial role in black hole physics. They allow physicists to study black holes from different perspectives, providing insights into their quantum properties and the nature of singularities. For example, the AD-CFT correspondence has been used to investigate the information paradox and the thermodynamics of black holes. In cosmology, dualities offer new ways to understand the early universe and the dynamics of cosmic inflation. They provide alternative descriptions of the same physical phenomena, leading to a deeper understanding of the fundamental processes that shape the cosmos. The mathematical structures underlying these dualities are complex and require advanced tools from algebra, geometry, and topology. The study of dualities has led to significant advancements in these mathematical fields, revealing deep connections between physics and mathematics. Dualities also have practical applications in other areas of physics. For example, the techniques developed to understand dualities in string theory have been applied to problems in condensed matter physics, leading to new insights into the behavior of quantum materials. The exploration of dualities continues to be a vibrant area of research. Physicists are constantly discovering new dualities and deepening our understanding of existing ones. These discoveries are crucial for advancing our knowledge of M-theory and the fundamental nature of the universe. As we uncover more about dualities, we gain a better understanding of the unity and coherence of the physical laws governing our universe. These insights bring us closer to a comprehensive theory of everything, integrating all forces and particles into a single, unified framework. Dualities in M-theory exemplify the power of theoretical physics to reveal hidden connections and unify disparate concepts. They provide a profound glimpse into the underlying structure of reality, showing that the universe is far more interconnected and intricate than previously imagined. The search for a theory of everything, or TUI, aims to unify all fundamental forces and particles into a single coherent framework. M-theory, with its dualities and higher dimensions, offers a promising approach to achieving this goal. One of the primary implications of M-theory for a TUI is the unification of gravity with the other fundamental forces. By incorporating gravity into a quantum framework, M-theory bridges the gap between general relativity and quantum mechanics. M-theory's ability to include all known particles and forces suggests that it could provide a comprehensive description of the universe. This unification would explain the interactions between particles at the smaller scales and the behavior of space-time at the larger scales. The higher dimensions in M-theory offer a way to resolve the apparent differences between the four fundamental forces. By compactifying these extra dimensions, different forces can emerge at lower energies, explaining why they appear distinct in our everyday experience. Dualities in M-theory provide powerful tools for understanding the connections between different physical theories. These dualities suggest that various string theories and other models are just different aspects of the same underlying reality, pointing towards a unified description of nature. The holographic principle, which emerges from M-theory, has significant implications for a TUI. It proposes that the information contained in a volume of space can be represented on its boundary, offering new ways to understand black holes and quantum gravity. M-theory's inclusion of branes and higher dimensional objects provides a richer framework for exploring the fundamental structure of matter. These objects can interact in complex ways, leading to new insights into the nature of particles and forces. The flexibility of M-theory in accommodating different compactifications and dualities means that it can potentially explain a wide range of physical phenomena. This adaptability is crucial for developing a TOE that can account for the diverse properties of the universe. M-theory also offers a framework for understanding the early universe and cosmic inflation. By describing the quantum behavior of space-time, it provides new models for the origin and evolution of the cosmos, addressing questions about the Big Bang and the structure of the universe. The mathematical consistency of M-theory, supported by its dualities and higher dimensions, suggests that it could provide a stable foundation for a TOE. This stability is essential for developing a theory that can withstand rigorous experimental and observational tests. One of the challenges for a TOE is explaining the observed values of the fundamental constants. M-theory's landscape of solutions, with its vast number of possible vacua, offers a way to explore why our universe has the specific properties it does. M-theory's potential to unify all forces and particles aligns with the goals of other approaches to a TOE, such as loop quantum gravity. By exploring the connections between these theories, physicists can gain a more comprehensive understanding of the fundamental principles governing the universe. The search for a TOE also has implications for our understanding of space and time. M-theory suggests that space-time is not a fixed background, but a dynamic, evolving entity shaped by quantum processes. This view challenges classical concepts and offers new ways to think about the fabric of reality. The pursuit of a TOE is not just a theoretical endeavor. It has practical implications for technology, cosmology, and our understanding of the universe. By developing a unified theory, scientists can gain deeper insights into the nature of matter, energy, and the fundamental forces that govern the cosmos. Ultimately, the implications of M-theory for a TOE highlight the profound interconnectedness of all physical phenomena. By unifying the fundamental forces and particles, M-theory offers a glimpse into the underlying unity of the universe, bringing us closer to a complete and coherent description of nature. Grand unified theories, or GUTs, are theoretical frameworks that aim to unify the three fundamental forces of the Standard Model: the electromagnetic force, the weak nuclear force, and the strong nuclear force. GUTs propose that these forces were once a single force in the early universe. One of the main motivations for GUTs is the observation that the strengths of the three forces appear to converge at high energies, suggesting they may have a common origin. This convergence is a key feature that GUTs attempt to explain. GUTs extend the Standard Model by introducing new symmetries and particles. These additional elements are necessary to unify the three forces into a single framework, often represented by larger symmetry groups such as SU5, SO10, or E6. A significant prediction of many GUTs is the existence of proton decay. Unlike the stable proton predicted by the Standard Model, GUTs suggest that protons can decay into lighter particles over extremely long timescales. Detecting proton decay would provide strong evidence for GUTs. GUTs also predict the existence of new particles, such as X and Y bosons, which mediate interactions between quarks and leptons. These particles are expected to be very massive and can only be produced at energy scales far beyond the reach of current particle accelerators. Another feature of GUTs is the explanation of the observed matter-antimatter asymmetry in the universe. GUTs can incorporate mechanisms, such as baryogenesis, that produce more matter than antimatter in the early universe, leading to the predominance of matter today. The concept of symmetry breaking is central to GUTs. In the high-energy conditions of the early universe, the unified force would have gradually separated into the distinct forces we observe today as the universe cooled and expanded. GUTs are often associated with supersymmetry, which proposes a symmetry between fermions and bosons. Supersymmetric GUTs provide a more elegant unification and can address some of the theoretical challenges faced by non-supersymmetric GUTs. One of the challenges for GUTs is the lack of direct experimental evidence. Proton decay has not been observed, and the predicted new particles have not been detected. This lack of evidence has led physicists to explore alternative models and to refine existing theories. Despite these challenges, GUTs remain an attractive area of research. They offer a way to unify the fundamental forces and provide a deeper understanding of the underlying principles of the universe. Ongoing experiments, such as those searching for proton decay, continue to test the predictions of guts. Guts also have implications for cosmology. They provide a framework for understanding the early universe's conditions, including the processes that led to the formation of the first elements and the evolution of cosmic structures. The mathematical structure of guts has led to advances in various fields, including group theory and particle physics. These theoretical developments have deepened our understanding of symmetry and the fundamental forces. Research into guts often intersects with other areas of theoretical physics, such as string theory and quantum gravity. These interdisciplinary efforts aim to develop a more comprehensive understanding of the universe's fundamental nature. The pursuit of guts reflects the broader goal of finding a theory of everything, which would unify all fundamental forces, including gravity. While guts do not include gravity, they are a crucial step toward this ultimate goal. As our experimental capabilities advance and new data become available, the prospects for testing and refining guts will improve. This ongoing research will help determine whether guts can provide a successful and comprehensive framework for unifying the fundamental forces of nature. The unification of forces is a central goal in theoretical physics, aiming to describe all fundamental interactions within a single, coherent framework. Historically, significant progress has been made by unifying the electromagnetic and weak nuclear forces into the electroweak force. In the 1970s, the electroweak theory, developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg, successfully unified electromagnetism and the weak force. This theory predicted the existence of the W and Z bosons, which were later experimentally confirmed, validating the unification. The strong nuclear force, which binds quarks together within protons and neutrons, remains distinct from the electroweak force at low energies. However, grand unified theories propose that at high energies, such as those present in the early universe, the strong force merges with the electroweak force into a single force. One of the key features of force unification is the idea that all forces were once unified at extremely high temperatures shortly after the Big Bang. As the universe cooled, these forces separated, or broke symmetry, resulting in the distinct forces we observe today. Supersymmetry, or SUSY, plays a crucial role in many unification theories. By introducing superpartners for every particle, SUSY helps to stabilize the interactions at high energies and allows for a more seamless unification of the forces. Theoretical models that include supersymmetry predict a more natural unification of the forces at high energy scales. These models often rely on larger symmetry groups, such as SU5 or SO10, to describe the unified force, which then breaks down into the familiar forces as the universe cools. Despite the elegance of these theories, direct experimental evidence for supersymmetry and force unification remains elusive. Large particle accelerators like the Large Hadron Collider continue to search for signs of supersymmetric particles and other indicators of force unification. The concept of unification extends beyond the forces described by the Standard Model. A theory of everything aims to include gravity as well, potentially unifying it with the other three fundamental forces within a single theoretical framework. String theory is a leading candidate for achieving this ultimate unification. By modeling particles as tiny, vibrating strings and incorporating additional dimensions, string theory provides a framework that can potentially unify all fundamental forces, including gravity. M-theory, an extension of string theory, further expands on this idea by suggesting an 11-dimensional universe where different string theories are viewed as different aspects of the same underlying theory. This approach offers a promising pathway towards the complete unification of forces. The pursuit of unification has led to significant advancements in both theoretical and experimental physics. It drives the development of new mathematical tools and inspires novel experimental techniques to test the predictions of these unifying theories. The unification of forces has profound implications for our understanding of the universe. It suggests that the diverse range of physical phenomena we observe can be traced back to a single, unified interaction, reflecting an underlying simplicity and coherence in the laws of nature. Research into force unification also has practical implications. Discoveries in this area could lead to new technologies based on a deeper understanding of the fundamental interactions, potentially revolutionizing fields such as energy production, materials science, and information technology. As our experimental capabilities continue to advance, we are likely to uncover more evidence supporting or refuting the various unification theories. Each discovery brings us closer to a more complete understanding of the fundamental forces and their unification. The ongoing quest to unify the forces represents one of the most ambitious and profound endeavors in science. It seeks to uncover the fundamental principles that govern the universe, providing a unified description of all known forces and particles, and offering new insights into the nature of reality itself. Proton decay is a significant prediction of many grand unified theories, which suggest that protons, usually considered stable, can decay into lighter particles. This process has profound implications for our understanding of particle physics and the stability of matter. In the standard model of particle physics, protons are considered stable because there is no mechanism for their decay. However, Guts propose that at high energies, the forces we know merge into a single force, which allows for processes like proton decay. Proton decay would involve the proton transforming into lighter particles, such as a positron and a neutral pion. This process requires extremely high energies and occurs over vast timescales, making it challenging to observe directly. The predicted lifetime of a proton in many guts is incredibly long, around 1031 to 1036 years. This is much longer than the current age of the universe, making proton decay a rare event. Detecting it requires highly sensitive and long-term experiments. Experiments designed to detect proton decay involve large volumes of matter, typically water or liquid scintillator, surrounded by sensitive detectors. These detectors are placed deep underground to shield them from cosmic rays and other background noise. One of the most notable experiments searching for proton decay is the Super Kamiokande detector in Japan. This detector consists of a vast tank of water surrounded by thousands of photomultiplier tubes, which detect the Cherenkov radiation produced by charged particles resulting from proton decay. Despite decades of searching, no definitive evidence for proton decay has been found. The non-detection of proton decay has helped to constrain the possible models of guts, pushing the predicted lifetime of the proton to longer timescales. The lack of observed proton decay does not rule out guts, but suggests that if proton decay occurs, it is an even rarer event than initially thought. This has led to refinements in theoretical models and increased the sensitivity of experimental searches. Proton decay, if observed, would provide strong evidence for the unification of forces. It would confirm that the electromagnetic, weak and strong nuclear forces are manifestations of a single, unified force at high energies. The discovery of proton decay would also provide insights into the early universe. It would support the idea that the conditions shortly after the Big Bang were governed by a unified force, influencing the formation and evolution of matter. Understanding proton decay could also help explain the matter-antimatter asymmetry in the universe. Guts often include mechanisms that produce more matter than antimatter, and proton decay could be linked to these processes, offering clues to this fundamental mystery. Continued efforts to detect proton decay involve not only improving existing experiments, but also developing new technologies and methodologies. Future detectors are expected to be even larger and more sensitive, increasing the chances of observing this rare event. Proton decay remains one of the most intriguing predictions of guts, representing a key test of these theories. Its discovery would mark a major milestone in particle physics, providing a deeper understanding of the fundamental forces and the nature of matter. The search for proton decay is a testament to the collaborative efforts of scientists around the world. It exemplifies the interplay between theory and experiment in the quest to uncover the fundamental principles of the universe. As experimental techniques continue to advance, the prospects for detecting proton decay improve. Each step forward in this search brings us closer to validating or refuting the predictions of grand unified theories and deepening our understanding of the cosmos. Grand unified theories propose various models to achieve the unification of the fundamental forces. Two of the most studied models are based on the symmetry groups, SU5 and SO10. These models offer different approaches to unifying the forces and predicting new particles and interactions. The SU5 model was one of the first grand unified theories proposed. It extends the standard model by embedding the SU3, XSU2, XU1 gauge groups into a single SU5 gauge group. This model predicts that the quarks and leptons can be unified into multiplets, meaning they are different manifestations of the same underlying entities. In the SU5 model, the proton decay is a key prediction. The unification of the gauge couplings implies that protons are not absolutely stable and can decay into lighter particles. This decay process is mediated by heavy gauge bosons known as X and Y bosons, which are predicted to exist at high energy scales. One of the main challenges for the SU5 model is that it does not naturally include neutrino masses. To incorporate neutrino masses, the model requires additional modifications or extensions, which can complicate the theoretical framework. The SO10 model is another prominent grand unified theory. It extends the SU5 model by using a larger symmetry group, SO10. One of the advantages of the SO10 model is that it naturally includes all fermions of one generation, including the right-handed neutrino, within a single multiplet. The inclusion of the right-handed neutrino in the SO10 model allows for a natural explanation of small neutrino masses through the seesaw mechanism. This mechanism predicts that the very small masses of the observed neutrinos result from the mixing between the light and very heavy right-handed neutrinos. The SO10 model also predicts proton decay, similar to the SU5 model. However, the predicted proton decay rate in the SO10 model can be different, depending on the specific details of the symmetry breaking and particle content. Both SU5 and SO10 models predict the existence of new particles and interactions at high energy scales. These new particles are typically very heavy and beyond the reach of current particle accelerators, but their effects might be detectable through rare processes such as proton decay. Another significant aspect of these models is the unification of gauge couplings. Both SU5 and SO10 models predict that the strengths of the electromagnetic, weak and strong forces converge at a high energy scale, known as the grand unification scale. The predictions of SU5 and SO10 models can be tested indirectly through their effects on low-energy observables. For example, precision measurements of the couplings of the standard model particles can provide hints about the validity of these unification models. The inclusion of supersymmetry in these models, resulting in SUSY guts, can address some of their challenges. Supersymmetric versions of SU5 and SO10 help stabilize the unification of gauge couplings and can provide dark matter candidates. Experimental searches for proton decay and other rare processes continue to provide critical tests for these grand unified theories. Large detectors, such as the proposed Hyperkamiokande, aim to improve sensitivity and potentially observe proton decay. The study of SU5 and SO10 models has also led to advances in mathematical physics, particularly in the understanding of group theory and symmetry breaking. These theoretical tools are essential for developing and refining grand unified theories. While SU5 and SO10 are among the most studied models, other symmetry groups like E6 and larger frameworks are also explored, offering different pathways to unification and new predictions for particle physics. The development and testing of these models are ongoing, with researchers seeking to reconcile theoretical predictions with experimental data. The pursuit of a grand unified theory remains a central goal in the quest to understand the fundamental forces of nature. Experimental searches for evidence of grand unified theories are among the most ambitious in particle physics. These searches focus on detecting rare processes like proton decay and exploring high-energy phenomena that might reveal new particles predicted by guts. Proton decay is a key prediction of many guts, but observing it is extremely challenging due to the predicted proton lifetime, which exceeds the current age of the universe by many orders of magnitude. Detecting proton decay requires massive detectors and long observation periods to capture these rare events. Hyperkamiokande in Japan is one of the leading experiments searching for proton decay. This detector uses a vast tank of ultra-pure water and thousands of photomultiplier tubes to detect Cherenkov radiation produced by the decay products of protons. Despite extensive searches, no proton decay events have been observed so far. The proposed Hyperkamiokande experiment aims to significantly increase the sensitivity to proton decay. By constructing an even larger detector with improved technology, Hyper-Kamiokande hopes to extend the limits on proton lifetime and potentially observe proton decay. Another approach involves using liquid scintillator detectors, such as the Juno experiment in China. These detectors can also search for proton decay by detecting the light emitted from the decay products. Liquid scintillator detectors offer complementary sensitivities to water Cherenkov detectors. High-energy particle colliders like the Large Hadron Collider, LHC at CERN, are crucial for probing energy scales where gut particles might exist. While current collider energies are below the predicted unification scale, they can still provide indirect evidence by observing deviations from the standard model predictions. The LHC has searched for signs of supersymmetry, which is often incorporated into guts. So far, no evidence of superpartners has been found, which pushes the possible mass scale for these particles higher and constrains gut models. Future colliders, such as the proposed Future Circular Collider, FCC, or the International Linear Collider, ILC, aim to reach higher energies and provide more precise measurements. These facilities could potentially discover new particles or interactions predicted by guts. Neutrino experiments also play a role in testing guts. Observations of neutrino oscillations and measurements of neutrino masses can provide clues about the seesaw mechanism and the presence of right-handed neutrinos, which are predicted by some gut models. Cosmological observations, such as the study of the cosmic microwave background and large-scale structure of the universe, offer indirect tests for guts. These observations can constrain the properties of the early universe, including the potential effects of gut-scale physics on cosmic inflation and matter-antimatter asymmetry. One of the major challenges in these experimental searches is distinguishing potential signals of guts from background noise. This requires highly sophisticated detection methods, rigorous data analysis, and extensive calibration to ensure the accuracy and reliability of the results. The rarity of the predicted phenomena necessitates large-scale international collaborations and substantial investment in infrastructure and technology. These collaborations bring together expertise from around the world to tackle the formidable challenges of gut research. Despite the lack of direct evidence so far, the constraints placed by these experiments are invaluable. They help refine theoretical models, exclude certain parameter spaces, and guide future research directions. The interplay between theory and experiment is crucial in the search for guts. Theoretical advancements can suggest new experimental techniques or observables, while experimental results can confirm, refute, or constrain theoretical predictions. As experimental capabilities continue to improve, the prospects for detecting signals of grand unified theories increase. Each new experiment brings the potential for groundbreaking discoveries that could revolutionize our understanding of the fundamental forces. The quest to experimentally verify guts is a testament to the human drive to understand the deepest principles of nature. It represents the cutting edge of particle physics and the ongoing effort to unify the fundamental forces into a coherent and comprehensive theory. The concept of holography in physics provides a profound way of understanding the relationship between gravity and quantum mechanics. It proposes that the information contained within a volume of space can be fully described by a theory that resides on the boundary of that space. Holography emerged from the study of black holes and was significantly advanced by the discovery of the ADS-CFT correspondence. This correspondence relates a gravitational theory in an anti-de Sitter, ADS space, to a conformal field theory, CFT, on its boundary. One of the most striking implications of holography is the idea that our three-dimensional universe could be a projection of information encoded on a distant, two-dimensional boundary. This is akin to a hologram, where a three-dimensional image is encoded on a two-dimensional surface. The ADS-CFT correspondence, proposed by Juan Maldacena in 1997, suggests that a string theory formulated in a five-dimensional ADS space is equivalent to a four-dimensional CFT without gravity. This duality provides a powerful tool for studying strongly coupled quantum systems. Holography has provided new insights into the nature of black holes. It helps resolve the black hole information paradox by suggesting that the information about matter falling into a black hole is not lost but encoded on the event horizon, the boundary of the black hole. This principle also has implications for understanding the entropy of black holes. The Bekenstein-Hawking formula relates the entropy of a black hole to the area of its event horizon, supporting the idea that the information content is proportional to the boundary area. Holography has profound implications for quantum gravity. It suggests that a complete theory of quantum gravity may be formulated without reference to a bulk spacetime, relying instead on a lower dimensional boundary theory. In cosmology, holography offers potential explanations for the initial conditions of the universe and the nature of cosmic inflation. It provides a framework for understanding how information from the early universe can be encoded in the cosmic microwave background. The concept of holography has also been applied to condensed matter physics. The ADS-CFT correspondence has been used to study strongly correlated electron systems, providing insights into high-temperature superconductors and other complex materials. Holography challenges traditional notions of space and time. It suggests that our perceived dimensions may be emergent properties, derived from more fundamental, lower-dimensional structures. Mathematically, holography relies on advanced tools from quantum field theory, general relativity, and string theory. It has led to significant developments in these areas, particularly in understanding the interplay between different physical theories. Experimental verification of holography remains a significant challenge. While direct evidence is difficult to obtain, indirect tests through the study of black holes, cosmic phenomena, and strongly correlated systems continue to provide valuable insights. Theoretical research in holography is ongoing, with physicists exploring new dualities and extending the principles of holography to other areas of physics. These efforts aim to deepen our understanding of the fundamental nature of reality. Holography also inspires new approaches to quantum information theory. The idea that information can be encoded in lower dimensions has implications for understanding quantum entanglement, entropy, and the foundations of quantum mechanics. As research progresses, the concept of holography may offer a path toward a unified theory that seamlessly integrates gravity with quantum mechanics. It represents a paradigm shift in our understanding of the universe, suggesting that the fabric of reality is far more interconnected and multifaceted than previously imagined. The ADS-CFT correspondence proposed by Juan Maldacena in 1997 is a powerful realization of the holographic principle. It posits a duality between a type of string theory in a five-dimensional anti-de Sitter space, or ADS, and a conformal field theory, or CFT, on its four-dimensional boundary. This duality suggests that the gravitational theory in ADS space can be fully described by the non-gravitational CFT on the boundary. The implications of this correspondence are profound, providing new tools for understanding both quantum field theories and gravity. One of the key features of the ADS-CFT correspondence is that it allows physicists to study strongly coupled quantum field theories using the gravitational theory in a higher dimensional space. This is particularly useful because solving strongly coupled field theories directly is often extremely challenging. In practical terms, ADS-CFT has provided insights into the behavior of quark-gluon plasma, a state of matter created in heavy ion collisions. By mapping the properties of the plasma to a dual gravitational theory, researchers have gained a deeper understanding of its dynamics. ADS-CFT also sheds light on the entropy of black holes. The correspondence suggests that the entropy of a black hole, which is proportional to the area of its event horizon, can be understood in terms of the degrees of freedom in the boundary field theory. The correspondence has applications in condensed matter physics as well. It has been used to model phenomena such as superconductivity and the quantum Hall effect, providing a new perspective on these complex systems. One of the most striking implications of ADS-CFT is the resolution of the black hole information paradox. According to the correspondence, information about matter that falls into a black hole is not lost, but encoded on the boundary of the ADS space, preserving unitarity in quantum mechanics. The mathematical framework of ADS-CFT involves advanced tools from both string theory and quantum field theory. These include techniques such as holographic renormalization and the use of correlation functions to map physical quantities between the two theories. The success of ADS-CFT has led to the exploration of other holographic dualities, extending the principles of the correspondence to different geometries and field theories. These generalizations continue to enrich our understanding of the fundamental connections between gravity and quantum mechanics. Despite its successes, there are limitations to ADS-CFT. The most well-understood cases involve highly symmetric, idealized systems, and applying the correspondence to more realistic, less symmetric situations remains a challenge. Experimental tests of AD-CFT are indirect, as the duality primarily provides a theoretical framework rather than direct predictions. However, insights gained from the correspondence have influenced experimental research in areas such as quark-gluon plasma and condensed matter systems. The study of AD-CFT is ongoing, with researchers continually discovering new aspects and applications of the duality. This includes exploring its implications for cosmology, such as the potential to model early universe conditions and inflation. AD-CFT has also inspired new developments in quantum information theory. The correspondence suggests deep connections between entanglement in the boundary field theory and the geometry of the bulk AD space, leading to the concept of entanglement entropy. As our understanding of AD-CFT deepens, it may provide further insights into the unification of quantum mechanics and gravity. The correspondence stands as one of the most significant advancements in theoretical physics, offering a powerful framework for exploring the fundamental nature of the universe. The AD-CFT correspondence continues to be a vibrant area of research, driving new discoveries and expanding our knowledge of both quantum field theory and gravitational systems. It exemplifies the profound interconnectedness of different areas of physics, highlighting the unity of the physical laws that govern our universe. Black hole thermodynamics is a field that explores the thermodynamic properties of black holes, drawing deep connections between gravity, quantum mechanics, and statistical mechanics. This area of study began with the pioneering work of physicists such as Stephen Hawking and Jacob Bekenstein. Bekenstein proposed that black holes possess entropy, which is proportional to the area of their event horizon. This idea was revolutionary, suggesting that black holes are not merely endpoints of gravitational collapse but have intrinsic thermodynamic properties. Hawking expanded on this idea by demonstrating that black holes emit radiation, now known as Hawking radiation. This radiation arises from quantum effects near the event horizon and implies that black holes can lose mass and energy over time, potentially evaporating completely. The temperature of a black hole, given by the Hawking temperature, is inversely proportional to its mass. This relationship indicates that smaller black holes are hotter and emit more radiation, while larger black holes are cooler. The laws of black hole mechanics closely resemble the laws of thermodynamics. The zeroth law states that the surface gravity of a black hole is constant across its event horizon, analogous to the uniform temperature in thermodynamic equilibrium. The first law of black hole thermodynamics relates changes in a black hole's mass, area, and angular momentum to changes in its energy, surface area, and charge. This law is akin to the first law of thermodynamics, which relates changes in energy to changes in entropy and work done. The second law, or Bekenstein-Hawking area theorem, states that the total area of a black hole's event horizon cannot decrease over time, similar to the second law of thermodynamics, which states that entropy in a closed system never decreases. The third law of black hole thermodynamics suggests that it is impossible to reduce the surface gravity of a black hole to zero through any physical process, analogous to the third law of thermodynamics, which states that absolute zero temperature cannot be reached. These parallels between black hole mechanics and thermodynamics hint at a deep, underlying connection between gravity and quantum mechanics. They suggest that the event horizon of a black hole encodes information about its internal states, similar to how entropy encodes information about the microstates of a thermodynamic system. The concept of black hole entropy has profound implications for the nature of information in physical systems. It raises questions about how information is preserved and transmitted, particularly in the context of the black hole information paradox. The holographic principle, which emerged from the study of black hole thermodynamics, proposes that all the information contained within a volume of space can be described by a theory on its boundary. This principle has broad implications for quantum gravity and the structure of space-time. Black hole thermodynamics also influences the study of quantum field theory in curved space-time. It provides insights into how quantum fields behave in the presence of strong gravitational fields, leading to a better understanding of particle creation and vacuum fluctuations. Research in black hole thermodynamics continues to be a vibrant field, exploring the connections between entropy, information, and the fundamental laws of physics. It drives ongoing efforts to reconcile general relativity with quantum mechanics. The study of black hole thermodynamics has also led to practical applications, such as the development of analog models in laboratories. These models simulate black hole horizons and provide experimental insights into Hawking radiation and other phenomena. As our understanding of black hole thermodynamics deepens, it may provide key insights into the nature of the universe, the fate of black holes, and the fundamental principles that govern the interaction between gravity and quantum mechanics. This field remains at the forefront of theoretical physics, offering tantalizing glimpses into the mysteries of the cosmos. The implications for quantum gravity arising from black hole thermodynamics are profound and multifaceted. They provide a unique window into the interplay between quantum mechanics and general relativity. One of the central implications is the realization that black holes must have a quantum description. The thermodynamic properties of black holes suggest that their microscopic states are governed by quantum mechanics. Hawking radiation implies that black holes are not entirely black, but emit particles due to quantum effects near the event horizon. This phenomenon requires a quantum field theory in curved spacetime and suggests that a full theory of quantum gravity must account for such effects. The entropy of black holes, proportional to the area of their event horizons, suggests a fundamental connection between gravity and information theory. This relationship indicates that a complete theory of quantum gravity must include a robust framework for describing the informational content of spacetime. The holographic principle, derived from black hole thermodynamics, posits that all information within a volume of space can be described by a theory on its boundary. This principle is a cornerstone for many approaches to quantum gravity, including string theory and loop quantum gravity. Black hole thermodynamics also impacts the understanding of spacetime singularities. The idea that entropy and information are preserved challenges traditional views of singularities and suggests that quantum gravity must resolve these infinities in a consistent manner. The black hole information paradox, which questions whether information that falls into a black hole is lost forever, drives much of the research in quantum gravity. Resolving this paradox requires a theory that integrates quantum mechanics with the geometric nature of spacetime. String theory addresses some of these implications by proposing that fundamental particles are not point-like, but are one-dimensional strings. This framework naturally incorporates the holographic principle and provides a way to describe the quantum states of black holes. Loop quantum gravity, another leading candidate for quantum gravity, suggests that spacetime is quantized and composed of discrete units. This approach aims to reconcile the discrete nature of quantum mechanics with the continuous fabric of spacetime described by general relativity. The study of black hole thermodynamics has also inspired new mathematical tools and techniques. Concepts like entanglement entropy, derived from quantum information theory, play a crucial role in understanding the quantum aspects of gravity. Experimental advances, such as the detection of gravitational waves, provide new ways to test the predictions of quantum gravity. Observations of black hole mergers and the properties of event horizons offer insights into the quantum structure of spacetime. Black hole thermodynamics challenges the traditional notion of locality in physics. The idea that information is encoded on a boundary surface suggests that spacetime itself might be an emergent phenomenon arising from more fundamental non-local principles. The implications for cosmology are also significant. Quantum gravity must account for the early universe's conditions, where both quantum effects and gravitational forces were extremely strong. Understanding black hole thermodynamics helps to model these extreme environments. The ongoing research in this field seeks to develop a coherent theory that unifies all fundamental forces, including gravity. This quest drives physicists to explore new ideas and frameworks, aiming to uncover the true nature of the universe at its most fundamental level. As our understanding of black hole thermodynamics and its implications for quantum gravity deepens, we move closer to answering some of the most profound questions in physics. The interplay between these fields continues to push the boundaries of knowledge, offering the promise of a unified theory that fully describes the workings of the cosmos. Current research directions in quantum gravity encompass a wide range of theoretical and experimental efforts. These efforts aim to deepen our understanding of the fundamental nature of spacetime and unify general relativity with quantum mechanics. One major direction involves the development and refinement of string theory. Researchers are exploring various aspects of string theory, including its mathematical structures, dualities, and implications for particle physics and cosmology. In particular, The study of the ADS-CFT correspondence continues to be a vibrant area of research. This duality provides a powerful tool for investigating strongly coupled quantum field theories and has applications in understanding black holes and condensed matter systems. Loop quantum gravity is another prominent approach being actively pursued. Researchers are working on better understanding the discrete structure of space-time, predicted by this theory, and its implications for the early universe, black holes, and cosmological evolution. Efforts are also underway to test the predictions of loop quantum gravity through observational and experimental means. This includes looking for signatures of quantum gravitational effects in the cosmic microwave background and gravitational wave data. The search for a consistent and complete theory of quantum gravity has led to the exploration of various alternative approaches. These include causal dynamical triangulations, asymptotic safety scenarios, and emergent gravity models, each offering unique insights into the nature of space-time. Researchers are also investigating the implications of quantum gravity for black hole thermodynamics and the information paradox. The goal is to resolve the paradox in a way that preserves the principles of quantum mechanics while incorporating the effects of gravity. Quantum information theory is playing an increasingly important role in quantum gravity research. Concepts like entanglement entropy and the holographic principle are providing new perspectives on the nature of space-time and the fundamental structure of the universe. Experimental efforts to detect signatures of quantum gravity include high-precision tests of general relativity, searches for violations of Lorentz invariance, and investigations into the nature of dark energy and dark matter. These experiments aim to uncover deviations from the predictions of classical gravity that could indicate quantum effects. Advances in observational technology, such as improvements in gravitational wave detectors and cosmic microwave background measurements, are providing new data that can be used to test theories of quantum gravity. These observations offer the potential to detect subtle effects predicted by these theories. The study of black holes remains a key focus in quantum gravity research. Researchers are examining the properties of black hole horizons, the nature of singularities, and the potential for quantum gravitational effects to resolve these extreme conditions. The interplay between quantum gravity and cosmology is another important research direction. Understanding how quantum gravitational effects influence the early universe, cosmic inflation, and the large-scale structure of the cosmos is crucial for developing a comprehensive theory. Collaborations between theorists and experimentalists are essential for advancing our understanding of quantum gravity. These collaborations help to design experiments, interpret data, and refine theoretical models based on observational evidence. Interdisciplinary approaches are also becoming more common, with researchers drawing on insights from quantum information theory, condensed matter physics, and mathematical physics to tackle the challenges of quantum gravity. As research progresses, the ultimate goal remains to develop a unified theory that seamlessly integrates quantum mechanics and general relativity. This theory would provide a complete and consistent description of all fundamental forces, offering profound insights into the nature of the universe and the laws that govern it. Twistor theory is an innovative approach to the problems of quantum gravity and the unification of fundamental forces. Developed by Roger Penrose in the 1960s, it provides a radically different perspective on space-time and the nature of particles. At its core, Twistor theory proposes that the fundamental objects are not points in space-time, but entities called twistors. These twistors encode information about the geometry of space-time in a way that is more aligned with the principles of quantum mechanics. Twistors transform space-time coordinates into complex numbers, offering a more natural framework for describing the geometry of light rays and null surfaces. This complex structure is key to understanding the deep connections between quantum theory and space-time. One of the major successes of Twistor theory is its ability to simplify the equations of general relativity and gauge theory. By reformulating these equations in Twistor space, many complex calculations become more manageable, revealing hidden symmetries and structures. Twistor theory also provides insights into the nature of space and time at the quantum level. It suggests that space-time might emerge from more fundamental twistor space, potentially resolving some of the inconsistencies between quantum mechanics and general relativity. In the context of particle physics, Twistor theory has been particularly influential in the study of scattering amplitudes. Edward Witten's 2003 twistor string theory proposed a new approach to calculating these amplitudes, leading to significant advances in new techniques. The application of twistor theory to scattering amplitudes has simplified calculations that were previously intractable. This has had a profound impact on our understanding of particle interactions and has led to the development of new computational tools. Twistor theory's elegant mathematical structure has also influenced string theory. It offers a different perspective on the fundamental objects and symmetries involved, suggesting new avenues for research and potential unification of forces. One of the key ideas in twistor theory is the concept of twistor space, which replaces conventional space-time coordinates with complex variables. This space provides a natural setting for the description of massless particles, such as photons and gluons. Twistor theory's approach to gravity involves reformulating Einstein's equations in terms of twistors. This has led to new insights into the nature of gravitational fields and the potential for a quantum theory of gravity that is fundamentally different from traditional approaches. The theory also offers potential solutions to the problem of quantum non-locality. By providing a framework where the geometry of spacetime is inherently linked to quantum properties, twistor theory suggests that non-local interactions might be more naturally understood. Despite its successes, twistor theory is not without challenges. One of the main difficulties is extending the theory to include massive particles and fully integrating it with the standard model of particle physics. Research in twistor theory continues to explore these challenges, with physicists developing new methods and extensions of the theory. These efforts aim to build a more comprehensive framework that can incorporate all known particles and forces. Twistor theory has also inspired a range of applications beyond fundamental physics. Its mathematical techniques have been used in fields such as integrable systems, complex geometry, and even aspects of computer graphics and signal processing. As our understanding of twistor theory deepens, it holds the potential to revolutionize our approach to quantum gravity and the unification of forces. By offering a fundamentally new perspective on space-time and quantum mechanics, twistor theory continues to push the boundaries of theoretical physics. Causal set theory is an approach to quantum gravity that proposes space-time is fundamentally discrete rather than continuous. This theory suggests that space-time is composed of a collection of discrete events, organized in a partially ordered set that reflects their causal relationships. The basic idea behind causal set theory is that the structure of space-time is determined by the order in which events occur. This causal order is the fundamental feature, while the familiar continuum of space-time emerges as an approximation at larger scales. In causal set theory, space-time points are replaced by elements of a causal set. Each element represents an event, and the partial order represents the causal relationships between these events, indicating which events can influence others. One of the key motivations for causal set theory is to address the problem of quantum gravity by avoiding the infinities that arise from treating space-time as a continuous entity. By discretizing space-time, causal set theory provides a natural cutoff at the smallest scales. This theory also offers a framework for reconciling the principles of quantum mechanics with the causal structure of general relativity. It maintains Lorentz invariance, meaning the physical laws are the same regardless of the observer's frame of reference, which is a crucial feature for any theory of quantum gravity. The concept of a causal set can be visualized as a network or graph, where the nodes represent events and the edges represent causal connections. This discrete structure replaces the smooth manifold of traditional spacetime. Causal set theory implies that the geometry of spacetime emerges from the underlying causal set. The macroscopic properties of spacetime, such as curvature and dimensionality, arise from the statistical properties of the causal set at large scales. One of the significant challenges in causal set theory is to recover the familiar continuum spacetime and the dynamics of general relativity from the underlying discrete structure. This involves showing how Einstein's field equations can be derived from the causal set framework. Researchers in causal set theory are also exploring how quantum phenomena, such as superposition and entanglement, can be incorporated into the causal set structure. This involves developing a quantum version of causal set theory that respects the principles of quantum mechanics. Causal set theory provides a new perspective on the nature of time. In this framework, time is fundamentally discrete, consisting of a sequence of events. This contrasts with the continuous flow of time in classical physics, and offers new insights into the nature of temporal evolution. The discreteness of causal sets also suggests new ways to think about black holes and singularities. In causal set theory, the singularities of general relativity might be resolved by the underlying discrete structure, potentially offering solutions to the problems of black hole entropy and the information paradox. Experimental tests of causal set theory are challenging due to the extremely small scales at which its effects would be significant. However, researchers are investigating potential observational signatures, such as modifications to the cosmic microwave background or deviations in the behavior of high-energy particles. Causal set theory has inspired a variety of mathematical and computational techniques for studying discrete structures. These tools are not only valuable for theoretical physics but also have applications in computer science, network theory, and other fields. The development of causal set theory is ongoing, with physicists and mathematicians working to refine the theory and explore its implications. This includes efforts to connect causal set theory with other approaches to quantum gravity, such as loop quantum gravity and string theory. As research progresses, causal set theory offers a promising avenue for understanding the fundamental nature of space-time. By proposing a discrete structure underlying the familiar continuum, it challenges our conventional notions of space and time and opens up new possibilities for unifying quantum mechanics and general relativity. The quest to understand the fabric of space-time continues to drive theoretical and experimental efforts. Causal set theory represents one of the many innovative approaches in this journey, providing unique insights and potential solutions to the profound mysteries of the universe. Non-commutative geometry is an approach that extends the concepts of geometry to spaces where the coordinates do not commute. This means that the order in which you multiply the coordinates matters, unlike in classical geometry where the multiplication of coordinates is commutative. This idea was introduced by Alain Connet in the 1980s as a way to understand spaces that are fundamentally different from the smooth manifolds of classical geometry. Non-commutative geometry provides a framework for describing the quantum properties of spacetime at very small scales. In non-commutative geometry, the traditional points of a space are replaced by operators on a Hilbert space. These operators do not commute, reflecting the inherent uncertainties in quantum behavior of spacetime at microscopic levels. One of the key motivations for non-commutative geometry is to address the incompatibility between general relativity and quantum mechanics. By modifying the structure of spacetime at small scales, non-commutative geometry offers a potential pathway to unify these two fundamental theories. Non-commutative geometry also provides tools for understanding gauge theories and the standard model of particle physics. It offers a natural framework for incorporating the symmetries and interactions of particles in a way that extends beyond classical geometry. A notable application of non-commutative geometry is in the formulation of quantum field theories. These theories often encounter difficulties at very high energies, but non-commutative geometry can regularize these infinities and provide a more consistent description. In the context of string theory, non-commutative geometry arises naturally when considering the effects of background fields on the dynamics of strings. This leads to non-commutative spaces where the coordinates of the strings do not commute, revealing new physical phenomena. Non-commutative geometry has also been applied to the study of black holes. By modifying the underlying geometry, it provides new insights into the nature of black hole singularities and the behavior of spacetime near these extreme objects. One of the fascinating aspects of non-commutative geometry is its ability to describe spaces that are fractal-like or have a complex, self-similar structure. This is in contrast to the smooth, continuous spaces of classical geometry. Researchers are exploring the implications of non-commutative geometry for cosmology. It offers potential explanations for the early universe's behavior, including the dynamics of cosmic inflation and the structure of spacetime at the Planck scale. Mathematically, non-commutative geometry involves sophisticated tools from operator algebras, functional analysis, and topology. These mathematical structures provide a rigorous foundation for understanding the non-commutative spaces. Experimental evidence for non-commutative geometry is challenging to obtain, as its effects are most prominent at scales far smaller than current experimental capabilities. However, indirect tests and theoretical consistency provide support for its validity. Non-commutative geometry has inspired new approaches to quantum gravity. By rethinking the fundamental nature of space and time, it offers alternative pathways to resolving the conflicts between general relativity and quantum mechanics. The development of non-commutative geometry is a collaborative effort involving physicists, mathematicians, and computer scientists. This interdisciplinary approach enriches the field and drives progress in understanding complex quantum systems. As research continues, non-commutative geometry holds the promise of providing deeper insights into the fundamental nature of reality. By challenging traditional notions of space and time, it opens new avenues for exploring the mysteries of the universe. The study of non-commutative geometry is part of the broader quest to understand the quantum structure of space-time. It represents an innovative and powerful approach, pushing the boundaries of knowledge and offering new perspectives on the fabric of the cosmos. Emergent gravity is a theoretical framework that suggests gravity is not a fundamental force, but emerges from more fundamental microscopic interactions. This idea contrasts with the traditional view that gravity is a basic interaction described by general relativity. The concept of emergent gravity draws parallels with phenomena in condensed matter physics, where macroscopic properties, like temperature and pressure, emerge from the microscopic behavior of atoms and molecules. In this framework, space-time itself can be seen as an emergent phenomenon. The geometry of space-time and the gravitational interactions we observe arise from the collective behavior of underlying degrees of freedom, much like the surface tension of water emerges from molecular interactions. One approach to emergent gravity involves thermodynamics. Jacob Bekenstein and Stephen Hawking showed that black hole entropy is proportional to the area of the event horizon, leading to the idea that space-time and gravity have a thermodynamic description. Ted Jacobson took this further by deriving Einstein's field equations from thermodynamic principles, suggesting that these equations are a macroscopic manifestation of more fundamental microscopic laws. This view positions gravity as an emergent rather than fundamental interaction. Emergent gravity also finds support in the holographic principle, which posits that the information content of a volume of space can be described by a theory on its boundary. This principle suggests that the three-dimensional dynamics we observe could emerge from two-dimensional microscopic physics. Eric Verlinder's entropic gravity theory is a notable model within emergent gravity. Verlinder proposed that gravity arises as an entropic force, driven by changes in the information associated with the positions of material bodies, further supporting the idea that gravity is an emergent phenomenon. In string theory, emergent gravity can be understood through the ADS-CFT correspondence. This duality shows how gravitational dynamics in a higher dimensional space can emerge from a lower dimensional quantum field theory without gravity, providing a concrete example of gravity emerging from more fundamental physics. Emergent gravity has implications for our understanding of dark matter and dark energy. If gravity is emergent, the effects attributed to dark matter might be explained by modifications to the emergent gravity framework, potentially offering new explanations for galactic rotation curves and cosmic acceleration. Research into emergent gravity is also exploring connections with quantum information theory. Concepts such as entanglement entropy are providing insights into how space-time and gravity might emerge from quantum entanglement among microscopic degrees of freedom. One of the challenges of emergent gravity is developing a detailed microscopic theory that fully explains how space-time and gravity emerge. This requires identifying the fundamental constituents and their interactions, which remain an active area of research. Experimental tests of emergent gravity are currently limited, but future observations of gravitational waves, black hole dynamics, and cosmological phenomena might provide evidence supporting or refuting emergent gravity models. The idea that gravity is emergent offers a new perspective on long-standing problems in physics, such as the nature of singularities and the unification of gravity with quantum mechanics. By viewing gravity as a macroscopic phenomenon, emergent gravity opens new avenues for theoretical exploration. Interdisciplinary research is crucial for the development of emergent gravity theories. Collaboration between physicists working in quantum mechanics, thermodynamics, information theory, and cosmology is essential for advancing our understanding of how gravity might emerge from more fundamental principles. Emergent gravity challenges traditional views and pushes the boundaries of our understanding of the universe. As research progresses, It has the potential to revolutionize our conception of gravity, space-time, and the fundamental forces, offering new insights into the nature of reality itself. The study of emergent gravity is part of the broader quest to understand the fundamental nature of the universe. By exploring how gravity could arise from deeper, more fundamental interactions, it provides a promising framework for unifying the forces of nature and unlocking the secrets of the cosmos. Quantum loop topography is an innovative approach in quantum gravity, aiming to describe the fabric of space-time at the smallest scales. This method extends the ideas of loop quantum gravity, focusing on the discrete nature of space-time. In loop quantum gravity, space-time is quantized into tiny loops, called spin networks. Quantum loop topography builds on this by exploring the topological properties of these spin networks, providing insights into the fundamental structure of space-time. Topography, in this context, refers to the study of the geometric properties and spatial relations of these loops, without concern for their exact shape or size. This helps in understanding how these fundamental loops connect and interact to form the fabric of space-time. One of the key concepts in quantum loop topography is the notion of spin foams. Spin foams are higher dimensional analogues of spin networks, representing the evolution of these networks over time. They provide a dynamic picture of how space-time evolves at the quantum level. By examining the topological features of spin foams, researchers aim to uncover how classical space-time emerges from these quantum structures. This involves studying how the loops and their connections change and evolve, leading to the smooth, continuous space-time we observe at macroscopic scales. Quantum loop topography also explores the role of topology in defining the properties of space-time. This includes understanding how different topological configurations of loops can lead to different physical phenomena, such as black hole formation or cosmic inflation. The approach is heavily mathematical, relying on tools from algebraic topology and differential geometry. These tools help in quantifying the topological properties of spin networks and spin foams, providing a rigorous framework for understanding quantum spacetime. One of the significant challenges in quantum loop topography is connecting the discrete, loop-based description of spacetime with the smooth, continuous description provided by general relativity. This involves finding a way to transition between the quantum and classical realms. Researchers are also investigating how quantum loop topography can address the problem of singularities. By understanding the topological structure of spacetime at the smallest scales, this approach offers potential solutions to the infinities that arise in classical general relativity. The study of black holes within the framework of quantum loop topography provides new insights into their quantum properties. It explores how the discrete loops might describe the event horizon and the entropy of black holes, contributing to the understanding of black hole thermodynamics. Quantum loop topography also has implications for cosmology. It offers a framework for understanding the early universe, including the quantum fluctuations that seeded the formation of galaxies and large-scale structures. Experimental tests of quantum loop topography are still in their infancy. However, advances in observational techniques, such as the detection of gravitational waves and precision measurements of the cosmic microwave background, offer potential ways to test the predictions of this theory. The interplay between quantum loop topography and other approaches to quantum gravity, such as string theory and non-commutative geometry, is an active area of research. This interdisciplinary effort aims to develop a more comprehensive understanding of quantum spacetime. Quantum loop topography is not just about describing the geometry of spacetime, but also about understanding its dynamics. This includes how spacetime loops interact and evolve, leading to the large-scale structure of the universe. As research progresses, quantum loop topography holds the promise of providing a deeper understanding of the quantum nature of spacetime. By focusing on the topological properties of loops and their interactions, it offers a novel perspective on the fundamental fabric of the cosmos. The study of quantum loop topography represents a frontier in theoretical physics, pushing the boundaries of our understanding of the universe. It combines advanced mathematical techniques with profound questions about the nature of reality, offering new insights into the quantum structure of spacetime. In this video, we explored the fascinating world of theoretical physics and the ongoing quest for a theory of everything. We began by discussing the definition and importance of a theory of everything, highlighting its potential to unify all fundamental forces and particles within a single framework. This journey took us through the historical context and origins of these ideas, as well as the current state of research in this exciting field. We delved into the foundational theories that paved the way, such as Newtonian mechanics, electromagnetism, and thermodynamics. These classical theories, while incredibly successful, showed limitations that led physicists to seek deeper, more comprehensive models. This quest brought us to the revolutionary concepts of special and general relativity, which redefined our understanding of space, time, and gravity. Next, we explored the intriguing realm of quantum mechanics, focusing on key principles like wave-particle duality, the Heisenberg uncertainty principle, and quantum entanglement. These ideas set the stage for more advanced theories like quantum field theory and the Standard Model of particle physics, which describe the interactions of fundamental particles. We then examined the cutting-edge theories that attempt to go beyond the Standard Model. String theory, with its concept of one-dimensional strings and higher dimensions, and loop quantum gravity, which quantizes space-time itself, were discussed in detail. We also looked at the role of supersymmetry and the ambitious efforts to unify all string theories under M-theory. Our journey included a look at alternative approaches such as causal set theory, non-commutative geometry, and emergent gravity. These theories offer unique perspectives and potential solutions to the challenges of unifying quantum mechanics and general relativity, pushing the boundaries of our understanding of the universe. Throughout the video, we touched on the experimental searches and challenges involved in testing these theories. From the detection of proton decay to the implications of holography and the ADC-CFT correspondence, these efforts highlight the interplay between theoretical predictions and experimental verification. We hope you enjoyed this deep dive into the fascinating quest for a theory of everything. If you found this video informative and engaging, please give it a like and subscribe to our channel for more content like this. Be sure to check out the rest of our videos, where we explore other intriguing topics in science and physics. Thank you for watching, and stay curious.